For as long as life has looked up, the moon has been there, a silent sentinel, rising and falling with the tides of time. But what if one night it simply vanished? No explosion, no noise, just gone. What would happen next? The moon, our eternal companion, has been part of Earth's story since the beginning. Its pale light has guided travelers, inspired poets, and marked the passage of time for countless generations. Every culture on Earth has woven the moon into their stories, their calendars, their understanding of the world. From ancient myths of lunar deities to modern scientific exploration, the moon has been a constant in our ever-changing world. When we look up at the night sky, we rarely pause to consider how profoundly the moon shapes our planet. Its gravitational embrace orchestrates our oceans, stabilizes our climate, and even affects the rhythm of life itself. The moon is not merely a decorative light in our sky, but a fundamental force that has helped create the conditions for life as we know it. The silvery glow of moonlight has illuminated our nights since before human eyes first gazed upward. It has been the silent witness to our evolution, our triumphs, our failures, our dreams. Countless lovers have whispered secrets beneath its glow, and wanderers have found their way by its light. The moon pulls at more than just our oceans. It tugs at our imagination, our sense of wonder, our connection to the cosmos. Its perfect circles and crescents have inspired art, mathematics, architecture, and philosophy. The recurring phases of the moon gave humanity its first reliable calendar, helping our ancestors track seasons and plan harvests. Without it, would we have developed the same understanding of time and cycles? Would our earliest civilizations have flourished in the same way? Our lunar companion moves in a cosmic dance with Earth, one that has continued for over 4 billion years. This partnership began in violence, when a Mars-sized object called Theia collided with the early Earth, sending debris spiraling into orbit that eventually coalesced into the moon. From catastrophic beginnings came a relationship that would ultimately nurture life and stability. Throughout human history, the moon has been imbued with meaning. Some saw the face of a man or a rabbit in its markings. Others saw the embodiment of feminine energy, cyclical change, or divine presence. The moon has been worshipped as a deity, studied as a scientific curiosity, and targeted as a destination for human exploration. Each culture has seen something different in its glow, but all have seen something significant. The moon's influence extends far beyond its light. Its gravitational pull creates the oceanic tides that rhythm our shorelines, shaping coastal ecosystems and human commerce alike. It stabilizes Earth's axial tilt, preventing the wild climatic swings that would make life as we know it impossible. The moon has even slowed Earth's rotation over billions of years, lengthening our days from just a few hours to the 24-hour cycle we experience now. What would it mean to lose such a companion? Not just practically, but emotionally and spiritually. The moon has been humanity's first stepping stone into the cosmos, our nearest neighbor in the vastness of space. It has represented both constancy and change, appearing reliable in its presence, yet ever shifting in its phase. To lose the moon would be to lose a fundamental reference point in our existence. In the stillness of night, when the world grows quiet, the moon offers a gentle reminder that we are not alone in the universe. Its reflected sunlight bridges the darkness, connecting us to the greater solar system beyond. For nocturnal creatures, it provides essential illumination. For humans, it offers comfort in the darkness, a familiar face that has watched over countless generations. As we begin this meditative journey through the possibilities of a moonless Earth, we invite you to consider not just what would happen, but what it would feel like to look up and find emptiness where that silver orb once hung. Join us as we explore the scientific, biological, cultural, and philosophical implications of the moon's absence, and perhaps gain a new appreciation for our silent companion while it still graces our sky. The moon was not just born with us, it helped shape the very Earth beneath our feet. Our story begins violently, approximately 4.5 billion years ago. The early solar system was a chaotic place where planetesimals, protoplanets, and cosmic debris orbited our young sun in unstable paths. Earth was forming, gathering mass, but it was not yet the planet we know today. Its fate would be dramatically altered by a cataclysmic event that astronomers call the Giant Impact Hypothesis. A Mars-sized planetary body, which scientists have named Theia, was on a collision course with our young Earth. When these two protoplanets met, the impact was so tremendous that it fundamentally reshaped both worlds. Theia did not simply crash and embed itself within Earth. The collision was so violent that much of Theia's mass merged with Earth, while enormous quantities of molten rock, metal, and vapor were ejected into orbit around our planet. This ejected material, a mixture of both Earth and Theia, began to cool and coalesce. Over thousands of years, these fragments gradually drew together through their own gravitational attraction, eventually forming what we now know as the Moon. This is why analyses of lunar samples brought back by Apollo astronauts revealed such striking similarities between moon rocks and Earth's mantle. They share a common origin, born of the same catastrophic embrace. Had this collision never occurred, Earth would be a vastly different place. Without the added mass from Theia, our planet would be smaller. The impact also likely contributed significant amounts of iron to Earth's core, enhancing our planet's magnetic field. This magnetic shield protects us from solar radiation and cosmic rays, creating conditions hospitable for surface life. Without the moon-forming event, Earth might never have developed the strong magnetic protection that allowed life to flourish. As the newly formed moon orbited Earth, it was much closer than it is today, perhaps just 14,000 to 16,000 kilometers away, compared to the average 384,000 kilometers that separate us now. At this proximity, the moon's gravitational influence on our planet was immensely stronger. This created tidal forces so powerful that they caused Earth's surface to bulge not just in the oceans, but in the land itself. These massive early tides acted like a brake on Earth's rotation. Our planet was spinning much faster then, with a day perhaps as short as 6 hours. The moon's gravitational drag gradually slowed this rotation, stretching our days to their current 24-hour length. This process continues even now, with Earth's rotation slowing by about 2.3 milliseconds per century, and the moon drifting approximately 3.8 centimeters farther away each year. The energy from this rotational slowing didn't simply disappear, it transferred to the moon, gradually pushing it into a higher orbit. This is why the moon continues its slow retreat from Earth, a cosmic dance that will continue for billions of years to come. In the distant future, if humanity or its descendants still inhabit Earth, they will look up at a moon that appears noticeably smaller in the sky than the one we see today. The stabilizing influence of the moon on Earth's rotation had profound implications for our planet's climate. Without a large moon, Earth would wobble much more dramatically on its axis. Our current axial tilt of approximately 23.5 degrees remains relatively steady thanks to the moon's gravitational influence, varying only slightly over thousands of years. This stability gives us our reliable seasons and climate patterns. Consider how different our world would be if Earth's axis could wobble chaotically between 0 and 85 degrees. As some scientific models suggest might happen without the moon's stabilizing presence. Seasons would become unpredictable, with some periods seeing no seasonal changes at all, and others experiencing extreme variations that would make agriculture and complex ecosystems nearly impossible to sustain. Mars provides a sobering example of what can happen to a planet without a large, stabilizing moon. The red planet's axial tilt has fluctuated dramatically over time, sometimes tilting as far as 60 degrees. These wild variations have contributed to Mars' extreme climate shifts and may have played a role in its transition from a warmer, wetter world to the cold desert we observe today. Earth, blessed with the moon's steadying presence, has been spared such chaotic climate swings. The moon's formation also likely played a role in Earth's early atmosphere. The tremendous energy of the impact that created the moon would have vaporized much of Earth's primitive atmosphere. This reset of atmospheric conditions may have been crucial for the later development of an atmosphere that could support life. The gravitational influence of the early, close moon might have also helped Earth retain its new atmosphere as it formed. preventing the lighter gases from escaping into space. The composition of Earth's core was also influenced by the Moon forming impact. The collision is believed to have generated enough heat to melt much of Earth, allowing heavier elements like iron and nickel to sink toward the center, while lighter materials floated toward the surface. This process, called differentiation, gave Earth its distinct layers: a metal-rich core, a silicate mantle, and a thin crust. The resulting structure has been crucial for the development of Earth's magnetic field and the eventual emergence of plate tectonics, both vital for life as we know it. As Earth and Moon settled into their cosmic dance, the Moon took on another role, that of celestial shield. The lunar surface bears the scars of countless impacts, a testament to the bombardment both Earth and Moon have faced over billions of years. By capturing some of this cosmic debris in its own gravitational field, the Moon has diverted numerous potential impacts away from Earth. Each crater on the lunar surface potentially represents an impact Earth was spared. The period known as the Late Heavy Bombardment, approximately 4 billion years ago, saw an intense barrage of asteroids and comets striking the inner solar system. The Moon's surface still bears the evidence of this violent epoch in the form of its largest impact basins. Had Earth weathered this storm alone, without the Moon absorbing some of the impacts, the development of early life might have been repeatedly disrupted or even prevented entirely. Even today, the Moon continues its protective role. While Earth's much stronger gravity means it attracts more objects, the Moon still intercepts some potential impactors. More importantly, the Moon's presence in Earth's vicinity has helped clear our orbital path of debris over billions of years, making our cosmic neighborhood somewhat safer than it might otherwise be. The Moon's influence extends even to Earth's oceans and how they've shaped our continents. The lunar-generated tides have been eroding coastlines and transporting sediments for billions of years. These tidal forces help drive ocean circulation patterns that distribute heat around the planet, moderating our climate and preventing more extreme temperature variations between the equator and the poles. Without the Moon, Earth's oceans would still experience tides due to the Sun's gravitational pull, but they would be much less pronounced, approximately 30% of their current magnitude. This reduction would dramatically alter coastal ecosystems that have evolved to thrive in the rhythmic exposure and submersion of tidal zones. The complex network of life that exists in tidal pools, estuaries, and salt marshes would never have developed as we know it. The relationship between Earth and Moon has also influenced the evolution of life itself. The predictable cycles of lunar phases gave early life forms reliable patterns of light and darkness, tidal ebbs and flows. Some scientists speculate that the intertidal zone, where lunar tides create a dynamic boundary between land and sea, may have been a crucial environment for the transition of life from ocean to land. Without strong tides, this transitional zone would be much smaller and less dynamic, potentially altering evolutionary pathways. As complex life evolved, lunar cycles became integrated into biological rhythms. Many marine organisms synchronize their breeding cycles with lunar phases. Corals release their reproductive cells in massive spawning events timed precisely to the lunar calendar. Certain species of sea turtles come ashore to lay eggs during specific moon phases when tides reach particular heights. Even some land animals and plants show sensitivity to lunar cycles in their behavior and growth patterns. The regular cycle of moonlight has also affected the evolution of predator-prey relationships, particularly for nocturnal species. Prey animals may be more vulnerable during the bright light of a full moon, while predators might gain hunting advantages. These pressures have shaped various adaptations, from the activity patterns of small mammals to the hunting strategies of owls and big cats. The rhythm of moonlight has been woven into the very fabric of Earth's ecological web. The moon has also served as Earth's first calendar, its regular phases marking the passage of time in a way that was visible and predictable to our ancestors. Many of humanity's earliest calendars were lunar-based, with months originally designed to track the approximately 29.5-day cycle from one new moon to the next. The moon gave humans their first reliable way to plan for the future, to anticipate seasonal changes, to coordinate social activities and agricultural practices. This celestial timekeeper shaped human culture in profound ways. Ancient megalithic structures like Stonehenge in England were carefully aligned to track lunar movements as well as solar ones. Civilizations from the Maya to the Chinese developed sophisticated lunar calendars. Religious festivals and holidays around the world are still timed to lunar phases, from Ramadan in Islam to Easter in Christianity to Diwali in Hinduism. The moon's gravity also affects Earth's mantle and crust, contributing to geological activity. While not as significant as the internal heat driving plate tectonics, lunar forces do create small but measurable strains in Earth's crust. Some research suggests that the timing of certain volcanic eruptions and earthquakes may be influenced by tidal forces, though these correlations remain an area of ongoing scientific investigation. Deep within Earth, even the liquid outer core may be subtly influenced by lunar gravity. Some scientists propose that tidal forces in the core could contribute to the circulation patterns that generate our planet's magnetic field. While the primary driver of Earth's geodynamo is convection from internal heat, lunar tidal effects might play a minor but complementary role in this complex system. The moon's presence has also been proposed as a factor in Earth's carbon cycle, which regulates our planet's temperature over geological timescales. The strong tides generated by the moon increase the mixing of ocean waters, potentially affecting how carbon dioxide is exchanged between the atmosphere and the deep ocean. This process helps buffer Earth against extreme temperature swings and has been part of maintaining our planet's long-term habitability. When we consider the moon's multifaceted role in Earth's development and ongoing processes, we begin to understand how profoundly its absence would alter our world. The moon is not merely Earth's accessory, but a fundamental partner in the complex systems that make our planet habitable. It has shaped our world's rotation, stabilized our climate, protected us from cosmic impacts, driven oceanic circulation, influenced biological evolution, and guided human cultural development. This partnership began in catastrophe but evolved into one of the most stable and life-nurturing relationships in our solar system. From the violence of collision emerged a planetary system uniquely suited for the development of complex life. The moon has been not just a witness to Earth's history, but an active participant in writing that history, its gravitational influence leaving an indelible mark on every aspect of our world. As we continue our journey, exploring what would happen if the moon disappeared, we carry with us this understanding of all it has done to shape Earth. The moon was not just born with us, it helped create us, in more ways than we typically acknowledge, as we gaze up at its familiar face in the night sky. The story of Earth and Moon is one of the most remarkable partnerships in our cosmic neighborhood, a relationship that has lasted billions of years and fundamentally shaped the only world we know that harbors life. With smaller tides, the oceans lose their rhythm, and the Earth begins to drift from the pattern it's always known. The relationship between the moon and Earth's oceans is one of the most visible manifestations of our satellite's influence. Anyone who has stood on a shoreline for several hours has witnessed this cosmic connection, as waters advance and retreat in the eternal rhythm of the tides. This ebb and flow, this liquid breathing of our planet, would fundamentally change if the moon were to vanish. To understand how profoundly the moon's disappearance would affect our oceans, we must first understand how lunar tides work. The moon's gravity pulls on every part of the Earth, but it's the oceans, liquid and free to move, that respond most dramatically to this gravitational embrace. As the Earth rotates, different parts of the ocean bulge toward the moon. This creates two tidal bulges, one on the side of Earth facing the moon, and another on the opposite side. The bulge facing the moon occurs because the moon's gravity pulls the water toward it. But why does water also bulge on the far side of Earth? This happens because the moon is actually pulling the solid Earth away from the water on the far side. The Earth, being a solid mass, moves as a single unit in response to the moon's pull, while the ocean can flow more freely, creating that second bulge. As Earth rotates through these bulges, coastlines experience the familiar cycle of high and low tides. Most locations on Earth experience 2 high tides and 2 low tides each day, though the exact pattern can be complicated by local geography, the shape of coastlines, and the depth of the ocean floor. The Sun also exerts a tidal force on Earth's oceans. Though the Sun is vastly more massive than the Moon, it's also much farther away. The result is that the Sun's tidal effect is about 46% as strong as the Moon's. When the Sun and Moon align during new and full moons, their tidal forces combine to create especially high and low tides, called spring tides. When they form a right angle to Earth during quarter moons, they partially cancel each other out, creating neap tides with less extreme water levels. Now imagine that the Moon suddenly vanished. The immediate change to our tides would be dramatic. Without the Moon's gravitational pull, we would be left with only the Sun's tidal force. Ocean tides would drop to roughly 30% of their current height. The rhythmic rise and fall of ocean levels would continue, but greatly diminished, like the muted breathing of a planet in shallow sleep. This reduction in tidal range would radically transform coastal environments around the world. Vast intertidal zones, those regions of shoreline that are submerged at high tide and exposed at low tide, would shrink dramatically. These areas are among the most biologically productive ecosystems on Earth, home to countless species that have evolved to thrive in the unique conditions created by the daily tidal cycle. Consider the rich diversity of life in a tide pool. Anemones, starfish, crabs, mollusks, and countless other organisms have adapted specifically to the alternating exposure to air and submersion in water. Their feeding, reproduction, and very survival depend on the predictable rhythm of the tides. Without the Moon, many of these intertidal zones would dry up completely or remain permanently submerged, eliminating these unique habitats. Mangrove forests, which grow in the intertidal zones of tropical coastlines, would face particular challenges. These remarkable ecosystems, with trees that can tolerate salt water and soil conditions that shift from submerged to exposed, serve as crucial nurseries for many marine species and protect coastlines from erosion and storm surges. The reduced tidal range would alter the extent and character of these forests, potentially leading to their decline in many regions. Without strong lunar tides, estuaries, where rivers meet the sea, would also change dramatically. The twice-daily mixing of fresh and salt water that characterizes these environments would be greatly diminished. Estuaries serve as critical nurseries for many fish species, with the tidal pulses helping to distribute nutrients and flush out pollutants. A moonless Earth would see these vibrant ecosystems simplified and reduced in their ecological function and diversity. Coral reefs, already under threat from climate change and ocean acidification, would face yet another challenge. Many coral species time their reproduction to the lunar cycle, releasing their eggs and sperm in synchronized mass, spawning events that coincide with specific moon phases. Without these lunar cues, coral reproduction might become less synchronized, potentially reducing successful fertilization rates and threatening the long-term viability of these ecosystems. The biological impacts extend far beyond these specific ecosystems. Many marine species use the predictable patterns of the tides for navigation, feeding, and reproduction. Shorebirds time their feeding to low tide, when mudflats are exposed and rich with accessible prey. Certain fish species move into flooded salt marshes during high tide to feed and spawn, retreating to deeper waters as the tide ebbs. Without the Moon, these intricate behaviors and migrations would be disrupted, forcing species to adapt or decline. Perhaps most dramatically affected would be those animals that navigate by the Moon or synchronize their reproduction with lunar cycles. Female grunion fish famously ride high spring tides onto Southern California beaches to lay their eggs in the sand, timing this precisely with the full and new moons. Sea turtles often nest during high spring tides, allowing them to reach safer positions higher on beaches. Without the Moon's influence, these carefully evolved behaviors would no longer match environmental conditions. The reduced tidal range would also change patterns of coastal erosion and sediment movement. Tides are powerful forces that shape our coastlines, eroding in some areas and depositing sediment in others. This continuous sculpting has created the coastal landscapes we know today. Without strong lunar tides, erosion patterns would shift, potentially destabilizing human settlements and infrastructure built with certain tidal ranges in mind. But the moon's influence on Earth's oceans extends far beyond coastal areas. Tides play a critical role in global ocean circulation, the vast system of currents that distributes heat and nutrients throughout the world's oceans. These currents are driven by various forces, including winds, density differences due to variations in temperature and salinity, and tidal energy. Particularly important are deep ocean currents, part of what oceanographers call the global thermohaline circulation, sometimes referred to as the ocean conveyor belt. This system moves enormous amounts of water around the planet, bringing warm water from the tropics toward the poles and cold water from the poles back toward the equator. This circulation helps regulate Earth's climate by redistributing heat, making northern Europe, for example, much warmer than it would be otherwise. Tidal forces contribute to this circulation by creating turbulence that helps mix different layers of the ocean. When tides move across underwater topographic features like ridges and seamounts, they generate internal waves and turbulence that bring deep, nutrient-rich water toward the surface. This mixing is crucial for marine productivity, bringing essential nutrients from the deep ocean into sunlit surface waters where photosynthesis can occur. Without the moon's tidal influence, this mixing would be significantly reduced. The result would likely be a more stratified ocean, with warmer surface waters less often mixed with cooler, nutrient-rich deeper waters. This could reduce the productivity of important fisheries and alter marine food webs. The changes to thermohaline circulation could also affect regional climates, particularly in places that depend on ocean currents for their moderate temperatures. Another consequence of reduced tidal mixing would be lower oxygen levels in deep ocean waters. The mixing, driven partly by tides, helps ventilate the deep ocean, bringing oxygen-rich surface waters downward. With less mixing, some deep ocean regions might experience expanded oxygen minimum zones, areas where oxygen concentrations are too low to support most marine life. This could compress the habitable volume of the oceans, with consequences rippling through marine ecosystems. Coastal human communities would face their own challenges in adapting to a moonless Earth. Throughout history, humans have built their societies around the predictable rhythms of the tides. Fishing communities time their activities to tidal patterns. Harbor operations depend on understanding the daily rise and fall of water levels. Coastal cities have built infrastructure designed for the specific tidal ranges of their locations. The sudden reduction in tidal range would require significant adaptations in all these areas. Some shallow harbors that were accessible only at high tide might become permanently inaccessible to larger vessels. Conversely, areas that were navigable only during high tide might become permanently navigable, potentially opening new shipping routes. Tidal power generation, an emerging renewable energy source, would become vastly less efficient or entirely non-viable, eliminating a promising clean energy option for coastal communities. The tides also play a subtle but important role in the global carbon cycle, which regulates Earth's climate. Coastal wetlands like salt marshes and mangroves are among the most efficient carbon sinks on the planet, sequestering atmospheric carbon at rates far higher than terrestrial forests. The regular flooding and draining of these ecosystems by the tides contributes to their high productivity and carbon sequestration capability. Reduced tidal range would likely diminish the extent and effectiveness of these natural carbon sinks. Tidal mixing also affects how much carbon dioxide the oceans can absorb from the atmosphere. The oceans have absorbed about 30% of human-released carbon dioxide, significantly slowing climate change. This absorption depends partly on mixing that brings surface waters, which exchange gases with the atmosphere, into the ocean depths where the carbon can be stored long-term. Reduced tidal mixing could potentially decrease this carbon sequestration, accelerating the buildup of greenhouse gases in the atmosphere. Beyond these physical and ecological effects, the loss of strong tides would alter something more ineffable: the experience of living near the sea. The rhythmic breathing of the oceans has inspired human art, literature, and philosophy for millennia. The tide's predictable yet ever-changing nature embodies cycles of renewal and transformation that have deep resonance in human consciousness. Without the moon driving strong tides, coastlines would become more static places, losing something of their dynamism and mystery. Consider the vast intertidal landscapes that temporarily emerge twice daily in places like Mont Saint-Michel in France or the Bay of Fundy in Canada, where tidal ranges can exceed 15 meters. These landscapes transform dramatically over just a few hours, creating ever-changing vistas that have captivated humans for generations. Without the moon, such dramatic tidal ranges would nowhere exist, and the boundary between land and sea would become more fixed, less magical in its fluidity. The ocean itself might become less predictable in other ways, however. The moon's gravitational influence actually has a stabilizing effect on ocean wave patterns. Computer models suggest that without the moon, wave heights might become more variable and extreme storm surges more common in some regions. The lunar rhythms that sailors have relied upon for millennia would give way to less predictable patterns driven solely by the sun and Earth's weather systems. For countless generations of seafarers, the relationship between the moon and tides has been essential knowledge. The ability to predict tides based on the moon's phases and position was crucial for safe navigation, especially in shallow coastal waters. Without the moon, navigation would need to rely more heavily on solar tides, which are less visually obvious from Earth, requiring more sophisticated instrumentation rather than direct observation of the night sky. The loss of the moon would also eliminate certain extreme tidal phenomena that occur in specific geographic locations. Tidal bores, for instance, are remarkable waves that travel upstream in certain rivers during incoming tides. The Qiantang River in China experiences one of the world's most impressive tidal bores, with waves sometimes reaching 3 meters in height, racing upstream at up to 40 kilometers per hour. These spectacular natural events, which have cultural and even touristic significance in some regions, would cease to exist. Some marine species would benefit from the moon's disappearance, particularly those that are vulnerable during extreme low tides. Certain coral reef organisms, for example, can suffer from exposure during unusually low spring tides that coincide with midday sun. Without the moon, such extreme low tides would no longer occur, potentially reducing this periodic stress. Similarly, species that have evolved defenses against predators that hunt by moonlight might find themselves with an advantage. Zooplankton, tiny drifting marine organisms that form the base of many ocean food webs, often migrate vertically in the water column to avoid predators, rising toward the surface to feed at night and descending to darker depths during the day. Many species adjust these migrations based on moonlight, staying deeper when the moon is full and bright. Without the moon, these behavioral patterns would shift, potentially changing predator-prey dynamics throughout marine ecosystems. The effect of the moon's disappearance on Earth's oceans would extend even to the deepest parts of the sea. The abyssal plains and trenches of the deep ocean might seem far removed from lunar influence, but even here, the moon's gravity exerts its pull. Deep sea tidal currents help distribute nutrients and oxygen through these remote environments. Without the moon, these currents would weaken, potentially affecting the strange and specialized creatures that inhabit Earth's final frontier. For the countless species that have evolved over millions of years in harmony with the rhythm of lunar tides, the moon's disappearance would represent an evolutionary crisis. Some would adapt, finding new cues for timing their life cycles or developing different reproductive strategies. Others would decline or face local extinctions, unable to adjust quickly enough to the changed conditions. The intricate web of relationships that define marine ecosystems would rewire itself in response to this cosmic absence. What emerges from this exploration of tides and oceans without the moon is a picture of profound change, not just to physical systems, but to the very character and rhythm of our planet. The biological pulse of coastal ecosystems, the chemical exchanges between air and sea, the very boundary between land and ocean, all would be transformed. With smaller tides, the oceans lose their rhythm, and the Earth begins to drift from the pattern it's always known. Without the moon's invisible grip, Earth begins to sway, not just in climate, but in chaos. Among the most profound, yet least immediately obvious effects of the moon's disappearance would be the gradual destabilization of Earth's axial tilt. This change would unfold over thousands of years, but its consequences would ultimately transform our planet in ways that would challenge the very foundations of life as we know it. Earth currently rotates with its axis tilted at approximately 23.5 degrees relative to its orbital plane around the Sun. This tilt gives us our seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer, while the southern hemisphere experiences winter, and vice versa. This reliable pattern has been a constant throughout human history and much of Earth's biological evolution. What many don't realize is that the moon plays a crucial role in maintaining this stable tilt. Like a cosmic stabilizer, the moon's gravitational pull prevents Earth from wobbling too dramatically on its axis. This stability has allowed for the relatively consistent climate patterns that have made our planet so hospitable to complex life. Without the moon's steadying influence, Earth's axial tilt would begin to change unpredictably. Computer models suggest that over thousands of years, Earth's tilt could vary anywhere from 0 to 85 degrees. Let us contemplate for a moment what this would mean for our world. Imagine Earth with no axial tilt, perfectly perpendicular to its orbital plane at 0 degrees. In this scenario, there would be no seasons at all. Every location on Earth would experience the same amount of daylight and darkness every single day of the year. The equator would remain hot, while the poles would remain permanently cold. The gradual transition of temperatures from equator to poles would create permanent climate bands around the planet. Without seasonal changes, many biological processes would be disrupted. Plants and animals that rely on seasonal cues for migration, hibernation, flowering, and reproduction would need to adapt rapidly or perish. The great migrations of birds, the hibernation of bears, the seasonal blooming of flowers, all evolved in response to the predictable rhythm of the seasons. Without these cues, ecosystems worldwide would undergo dramatic reorganization. Now imagine the opposite extreme, an Earth tilted at 85 degrees, nearly on its side, relative to its orbital plane. In this scenario, seasons would become unimaginably extreme. Each pole would face almost directly toward the Sun for one part of the year, experiencing constant daylight and intense heating, then face almost directly away from the Sun 6 months later, plunging into perpetual darkness and freezing conditions. Even temperate and equatorial regions would experience radical seasonal swings. Places that currently enjoy moderate climates might see temperatures soar to uninhabitable levels during their summer and plunge far below freezing in their winter. The equator would no longer be consistently warm, but would instead experience dramatic seasonal variations like nowhere on our current Earth. The most alarming aspect of a moonless Earth's axial instability is not just the potential extremes, but the unpredictability of the changes. The tilt wouldn't simply jump to 0 or 85 degrees and stay there. Instead, it would wander chaotically between different angles over periods of thousands to tens of thousands of years, never settling into a stable pattern. This chaotic wobbling would create an environment in which long-term climate patterns become impossible to predict. Species would face constantly changing selection pressures, making evolutionary adaptation extremely difficult. The predictable climate niches that allow for specialized adaptations would disappear, favoring only the most generalist species that can tolerate extreme variability. Human civilization has flourished during a period of unusual climate stability. Our agriculture, infrastructure, and settlement patterns all developed under the assumption of relatively predictable seasons and climate zones. Without the moon, this foundation of civilization would slowly crumble as Earth's axial tilt began its chaotic dance. Agricultural systems would face particular challenges. Crops have been carefully selected and bred for for specific growing seasons and climate conditions. As these conditions became increasingly unpredictable, food security would be threatened. Imagine planning for planting when you cannot predict if the coming season will bring drought, flood, heat, or frost. The agricultural calendar that has guided human food production for millennia would lose its reliability. The great forests that serve as Earth's lungs would also struggle to adapt to such variable conditions. Trees, with their long life cycles, are particularly vulnerable to rapid climate changes. Forest boundaries would shift, contract, and expand in response to the changing tilt, but many ancient forest ecosystems might not survive the transition. The loss of these carbon sinks would further exacerbate climate instability. Ocean currents, which play a critical role in distributing heat around our planet, would be repeatedly reorganized as the axial tilt shifted. The predictable currents that sailors have navigated for centuries would become increasingly variable. Marine ecosystems structured around these currents would face disruption, affecting fisheries and marine biodiversity. The jet streams, those high-altitude air currents that influence weather patterns across continents, would also change their behavior as the axial tilt varied. Weather patterns would become increasingly difficult to predict, with some regions experiencing unprecedented storms, droughts, or temperature extremes as atmospheric circulation adjusted to the changing distribution of solar heating. Ice caps and glaciers would advance and retreat dramatically as the tilt shifted. During periods of extreme tilt, one pole might lose its ice cap entirely, while the other grew to cover much more of the hemisphere. The resulting changes in sea level would repeatedly redraw coastlines, forcing coastal communities to either adapt through massive engineering projects or abandon vulnerable areas. The hydrological cycle, the movement of water between the atmosphere, land, and oceans, would also be disrupted by these changes. Rainfall patterns would shift unpredictably as atmospheric circulation responded to the changing distribution of solar energy. Rivers might periodically dry up or flood as their watersheds experienced these shifting precipitation patterns. Aquifers would be depleted in some regions and recharged in others, altering groundwater availability. These physical changes would trigger cascading effects through Earth's ecosystems. Food webs, the complex networks of who eats whom, would be repeatedly disrupted as some species adapted to the changing conditions while others declined. Keystone species, those that have disproportionate effects on their ecosystems, might be lost, triggering fundamental reorganizations of ecological communities. Biodiversity would likely decline overall, with each dramatic shift in axial tilt causing extinction events. The most vulnerable would be specialist species adapted to narrow ecological niches, as well as those with limited geographic ranges or slow reproductive rates that limit their adaptive capacity. The Earth might transition toward ecosystems dominated by generalist species with high reproductive rates and broad environmental tolerances, perhaps resembling the ecological patterns seen after previous mass extinction events. For humans, adapting to this new reality would present unprecedented challenges. Our civilizations have been built on the assumption of climate stability. Our cities are located where they are because of dependable water sources, agricultural potential, or navigable waters, all of which could change as the axial tilt varied. Infrastructure designed for current climate conditions, from irrigation systems to flood defenses to heating and cooling systems, would become increasingly mismatched to the changing environment. Migration would likely become a recurring feature of human society. As previously habitable regions became unlivable and new opportunities opened elsewhere, such large-scale movements of people would stress social and political systems, potentially leading to conflict over resources and territory. The very concept of national boundaries, often aligned with geographic features that derive from current climate patterns, might need to be reimagined in this more fluid world. Knowledge systems would also need to adapt. Traditional ecological knowledge, built up over generations of observation of local conditions, would become less reliable as those conditions changed unpredictably. Scientific understanding would need to shift from prediction based on historical patterns to more dynamic models capable of anticipating chaotic variations. Some might wonder if technology could provide solutions to these challenges. Could we, for instance, construct massive sunshades in space to compensate for the extreme variations in solar heating? Could we build artificial environments protected from the vagaries of the changing climate? While such approaches might offer limited protection for some humans and certain carefully selected species, the scale of the changes would likely overwhelm even our most ambitious technological interventions. The psychological impact of living on a planet with such unpredictable long-term climate patterns would be profound. Humans have evolved in an environment with reliable seasonal rhythms. Our bodies and minds are attuned to these cycles, from seasonal affective disorder to traditional celebrations marking the changes of seasons. Living in a world where the very rhythm of the year became increasingly unpredictable would require fundamental adaptations in how we conceptualize time and plan for the future. Let us consider for a moment what adaptations might evolve in response to these conditions. Species with short generation times would have advantages, as they could respond more quickly to changing selective pressures. Phenotypic plasticity, the ability of an organism to change its characteristics in response to environmental conditions without genetic changes, would be strongly favored. We might see the evolution of broader tolerance ranges and more generalized diets and habitat requirements. For plants, strategies might include maintaining large seed banks that could lie dormant until favorable conditions returned, or developing extremely efficient dispersal mechanisms to colonize newly suitable habitats. For animals, we might see the evolution of extreme mobility to track shifting climate zones, or the ability to enter extended dormant states to survive periods of unfavorable conditions. Human societies would likely become more nomadic or develop modular, relocatable infrastructure. Knowledge systems would place greater emphasis on adaptability and resilience rather than optimization for specific conditions. Cultural values might shift toward flexibility and broad competence rather than specialized expertise. The night sky would also change as Earth's tilt varied. The stars visible from any particular location would shift as the orientation of Earth relative to the celestial sphere changed. Constellations that were visible year-round might become seasonal, while some stars never before seen from certain latitudes would become visible. The cosmic reference points that have guided human navigation and timekeeping for millennia would need to be reinterpreted. Over even longer timescales, the unstable axial tilt could affect Earth's potential to maintain habitable conditions at all. Earth currently orbits in the Sun's habitable zone, the region where temperatures allow for liquid water on the surface. However, this habitability depends partly on our moderate and stable axial tilt. With extreme tilts, parts of the planet could experience temperatures that temporarily push them outside habitable ranges, even if the average global temperature remained moderate. Looking to other planets in our solar system provides some perspective on the importance of axial stability. Mars, with its small and distant moons that provide minimal stabilizing influence, has experienced dramatic changes in its axial tilt over time. These changes are believed to have contributed to the loss of much of Mars's atmosphere and its transition from a warmer, wetter world to the cold desert we see today. Without the moon, Earth might face a similar, if less extreme, fate over billions of years. Venus, rotating slowly and in the opposite direction to most planets, may have experienced a chaotic history of axial changes that contributed to its current inhospitable state. While Earth would not become as extreme as Venus without the moon, the comparison reminds us how precarious planetary habitability can be when rotational stability is lost. It's worth noting that the changes we've described would unfold gradually over thousands to millions of years. If the moon were to somehow vanish tomorrow, we wouldn't wake up to a world of chaotic seasons the next day. The initial changes would be subtle, detectable primarily through precise scientific measurements rather than casual observation. It would be our distant descendants, perhaps hundreds of generations from now, who would face the full consequences of living on an unstable Earth. This gradual timeline might create a dangerous situation where the early warning signs could be easily overlooked or dismissed. By the time the changes became obvious enough to trigger widespread concern, the momentum of the destabilization would be difficult to address. This highlights the importance of long-term thinking and planetary stewardship, recognizing that the stability we take for granted depends on cosmic relationships established billions of years ago. The relationship between Earth and Moon represents one of the most significant planetary partnerships in our solar system. Like dancers who have moved together for billions of years, they have established a rhythm and balance that has allowed life to flourish. Without the Moon's steadying hand, Earth would begin a new and more chaotic dance, one that would challenge the resilience of even the most adaptable forms of life. As we contemplate this scenario, we gain a deeper appreciation for the delicate cosmic circumstances that have made our planet so conducive to complex life. The Moon is not merely an ornament in our night sky or a subject for poetry and romance. It is a critical component of Earth's life support system, a silent partner in maintaining the stable conditions that have allowed consciousness itself to emerge and contemplate its own existence. Without the Moon's invisible grip, Earth begins to sway, not just in climate, but in chaos. And in that swaying, we glimpse the profound interconnectedness of our planet with the wider cosmic environment in which it exists. As the days grow shorter, time itself begins to feel unfamiliar. In the cosmic dance between Earth and Moon, one of the most fundamental yet least appreciated aspects is how our satellite has shaped the very rhythm of our days. The 24-hour cycle that governs human life, that divides our existence into periods of light and darkness, work and rest, has been profoundly influenced by the Moon's gravitational embrace. If the Moon were to disappear, this ancient rhythm would begin to change, initially imperceptibly, but eventually dramatically. To understand this change, we must first look back in time. When Earth first formed about 4.5 billion years ago, it was spinning much faster than it does today. Scientists estimate that a day on the newly formed Earth may have lasted only about 6 hours. Over billions of years, the Moon has acted as a gravitational brake on Earth's rotation, gradually slowing it down to the 24-hour day we experience now. This braking action occurs through tidal forces. The Moon's gravity creates tidal bulges in Earth's oceans, and to a lesser extent, in the solid Earth itself. As Earth rotates, these bulges move across the planet's surface. Because they're pulled slightly ahead of the direct Earth-Moon line by Earth's rotation, they exert a gravitational torque on Earth, gradually slowing its spin. The energy lost from Earth's rotation doesn't simply disappear, but is transferred to the Moon, gradually pushing it farther away from Earth. Without the Moon's presence, this braking effect would cease. Instead of continuing to slow down, Earth's rotation would be influenced by other factors. The Sun exerts its own tidal forces on Earth, though they're weaker than the Moon's. Various other forces, including the redistribution of mass within Earth due to glacial melting or tectonic activity, can also subtly affect rotation speed. The net result, according to scientific models, would be that Earth's rotation would gradually accelerate over millions of years. Without the Moon's braking influence, a day might eventually shorten to 6 to 12 hours. This change would be extremely gradual from a human perspective, perhaps a millisecond or less per year, but over geological time, the impact would be profound. What would life be like on an Earth with days half as long as what we experience now? The implications would ripple through every aspect of our planet's physical systems and the life that depends on them. Consider first the physical effects. Shorter days would mean less extreme temperature variations between day and night, as the planet would have less time to heat up during daylight hours and less time to cool during darkness. This could reduce the thermal stress on some ecosystems, but might disrupt weather patterns that depend on these daily temperature cycles. Earth's faster spin would increase the Coriolis effect, the apparent deflection of moving objects caused by the planet's rotation. This would alter global wind patterns and ocean currents, potentially shifting climate zones and precipitation patterns across the planet. Hurricanes and cyclones might become more intense or form in regions where they rarely occur today. As the stronger Coriolis force would contribute to their circulation, The distribution of Earth's mass would also change slightly as the planet spun faster, causing it to bulge more at the equator and flatten more at the poles. This redistribution of mass would affect Earth's gravitational field, potentially altering sea levels in different regions. While these changes would be subtle from a human perspective, they would have cumulative effects on coastal ecosystems and human settlements. But perhaps the most profound impacts would be on living organisms, which have evolved over millions of years to synchronize with Earth's 24-hour cycle. This synchronization is encoded in the circadian rhythms that govern countless biological processes, from sleep-wake cycles to hormone production, cell repair, and even gene expression. Plants would face particular challenges. Many plant species carefully time their metabolic activities to the daily cycle of light and darkness. Photosynthesis occurs during daylight hours, while other essential processes happen during the night. A shorter day-night cycle would force plants to adapt these carefully balanced rhythms. Some might struggle to complete their nocturnal processes in a shorter night, while others might not receive enough continuous daylight for optimal photosynthesis. Consider the phenomenon of photoperiodism, where plants use the relative lengths of day and night to determine seasonal changes and time critical activities like flowering. In a world with 8-hour days, the traditional signals that trigger these responses would be fundamentally altered. Plants that flower based on specific day lengths might bloom at inappropriate times, disrupting their relationships with pollinators and potentially affecting their reproductive success. Animals would face their own set of challenges. Most animal species have strong circadian rhythms that govern when they sleep, hunt, feed, and engage in other essential activities. These rhythms are not infinitely adaptable, having evolved over millions of years to align with Earth's 24-hour cycle. A shift to significantly shorter days would force a profound reorganization of these basic behavioral patterns. Mammals, including humans, would perhaps struggle the most with this change. Our sleep patterns, hormone cycles, and metabolism are all deeply attuned to the 24-hour day. The human body anticipates the alternation of day and night through the production of hormones like melatonin, which helps regulate sleep. Our core body temperature, blood pressure, cognitive performance, and countless other physiological parameters fluctuate according to this internal clock. Imagine trying to maintain healthy sleep patterns in a world with 8-hour days. Would humans adapt by taking multiple shorter sleep periods? Or would we attempt to stay awake for multiple days before sleeping for a longer period? Either approach would require a fundamental rewiring of our biological rhythms. The mismatch between our evolved circadian cycles and the new planetary rhythm could lead to chronic sleep disruption, with cascading effects on physical and mental health. For nocturnal animals, shorter nights would mean less time to hunt, feed, and perform other essential activities. Diurnal species would similarly find their active periods compressed. The boundaries between diurnal and nocturnal niches might blur, forcing species that currently avoid competition by being active at different times to suddenly find themselves in direct competition for resources. The impacts on animal reproduction could be equally profound. Many species time their breeding to specific day lengths that signal favorable seasons. Birds, for instance, often use increasing day length in spring as a cue to begin breeding activities. In a world with radically different day-night cycles, these carefully evolved timing mechanisms would no longer provide reliable information about seasonal conditions. Even marine life, much of which lives in the relative darkness of the deep ocean, would be affected. Many marine species engage in vertical migration, moving toward the surface at night to feed and back to depths during the day to avoid predators. These migrations, crucial for oceanic food webs, are timed to the daily cycle of light and darkness. Shorter days would compress these migration periods, potentially disrupting feeding opportunities. The interaction between shortened days and changing seasons would create further complexity. Seasons themselves would still exist due to Earth's axial tilt, but the experience of them would be altered. Each season would contain many more day-night cycles than before. Instead of about 90 days and nights per season, there might be 180 or more. The psychological experience of time passing would be fundamentally changed, with each season feeling subjectively longer because of the increased number of day-night transitions. For humans, the cultural and social implications would be enormous. Our entire civilization is structured around the 24-hour day. Work schedules, school hours, transportation timetables, entertainment, religious observances, all are calibrated to this fundamental rhythm. A significant shortening of the day would force a reimagining of these basic social structures. Would human society adapt by creating new time divisions? Perhaps days would be redefined to include multiple day-night cycles, preserving some of our existing social patterns. Or perhaps we would fully embrace the new rhythm, developing entirely new cultural practices and social organizations better suited to the accelerated cycle of light and darkness. Technology might offer partial solutions. Artificial lighting already allows humans to extend activities into natural darkness, and climate-controlled buildings buffer us from the direct experience of the external environment. These technologies might be leveraged to create artificial day-night cycles that better match our biological needs, even as the natural cycle shifted to a faster rhythm. Yet such technological adaptations would be available only to some portions of humanity, likely deepening existing inequalities. They would also further separate humans from the natural rhythms of the planet, potentially exacerbating the sense of disconnection from nature that many already experience in highly technological societies. The experience of time itself would change in subtle but important ways. Humans evolved within the 24-hour rhythm, and our perception of time passing is calibrated to this cycle. Many languages divide future and past into units based on the day, from tomorrow and yesterday to expressions like a fortnight or a month of Sundays. As the fundamental unit of the day changed, these linguistic and psychological structures would need to adapt as well. For many organisms, including humans, the change would likely be too rapid for evolutionary adaptation. While small adjustments to circadian rhythms can occur relatively quickly, a halving of the day length would outpace the ability of most species to evolve matching biological clocks. Instead, plants and animals would have to accommodate the mismatch between their internal rhythms and the external cycle, likely at significant physiological cost. Some species might fare better than others. Those with shorter generation times could adapt more quickly through natural selection. Others might possess greater phenotypic plasticity, the ability to adjust their physiology and behavior within a single lifetime. These adaptable species would have substantial advantages as the day length changed, potentially leading to shifts in ecosystem composition and function. Over longer timescales, the changing day length would interact with the shifts in Earth's axial stability discussed earlier. The combination of chaotically shifting seasons and steadily shortening days would create an environment of temporal unpredictability unlike anything experienced in Earth's recent history. Ecosystems would likely become simpler, dominated by generalist species with high adaptability and tolerance for variable conditions. It's worth noting that the scenario we've explored, with days shortening to 6 to 12 hours, would unfold over millions of years. The immediate effect of the moon's disappearance would be imperceptible to human experience, with perhaps only atomic clocks detecting the subtle change in Earth's rotation rate. Each human generation would experience virtually the same day length as the previous one, with the changes accumulating over geological rather than historical time. This gradual pace means that life would have some opportunity to adapt, though the change would still likely outpace evolutionary processes for many species. It also means that human civilization would have time to recognize the pattern and potentially develop technological or cultural adaptations to mitigate its effects. Perhaps most significantly, the changing day length would serve as a constant reminder of the moon's absence. Each subtle acceleration of Earth's rotation would be a testament to the missing gravitational embrace that had, for billions of years, help create the temporal rhythm that life on Earth had come to take for granted. The experience would be one of temporal uncoupling, a gradual drift away from the cosmic rhythm that had shaped life since its beginnings. As the days grew shorter, time itself would begin to feel unfamiliar, a reminder of how profoundly the moon had shaped not just our planet, but our experience of existing upon it. Life dances to the moon's rhythm. Without it, some songs may go silent. The relationship between Earth's living beings and the moon reaches far deeper than most of us realize. It extends beyond the obvious influences of moonlight and tides to shape the very reproductive cycles, behaviors, and evolutionary paths of countless species. If the moon were to vanish, the biological consequences would ripple through ecosystems worldwide, from the deepest ocean trenches to the highest mountain forests, affecting life in ways both subtle and profound. Perhaps the most visible impact would be on organisms that have evolved to synchronize their reproduction with lunar cycles. Many marine creatures in particular have developed precise timing mechanisms key to the phases of the moon, creating some of nature's most spectacular reproductive events. Consider the remarkable phenomenon of corals spawning on the Great Barrier Reef. Once a year, typically after the full moon in late spring or early summer, many species of coral simultaneously release their eggs and sperm into the water in a synchronized reproductive event of breathtaking scale. This mass spawning, described by witnesses as an underwater snowstorm, depends on the coral's ability to detect the specific lunar phase. Without the moon's guiding light and gravitational cues, this synchronization would be lost. Why does this timing matter? Synchronization increases the chance of successful fertilization for broadcast spawners like corals, which release their gametes into the water rather than mating directly. It also creates a temporary abundance that satiates predators, allowing a greater percentage of eggs and larvae to survive. Without the moon to coordinate this timing, coral reproduction would become haphazard, potentially reducing fertilization rates and larval survival, further threatening these already vulnerable ecosystems. Similar lunar timing is seen in many other marine creatures. Pololo worms in the South Pacific time, their reproductive swarming to specific moon phases, rising to the surface in such numbers that they have traditionally been harvested as a seasonal delicacy by local populations. Various species of crabs, sea urchins, and fish also coordinate their breeding with lunar cycles. The loss of this synchronization would disrupt reproduction in these species, potentially leading to population declines or shifts in marine community composition. One of the most visible and well-studied examples of lunar-influenced reproduction involves sea turtles. Female sea turtles typically come ashore to lay their eggs during the night, often preferring times around the full moon when higher tides allow them to reach further up the beach, and when sufficient light facilitates navigation. The hatchlings, when they emerge weeks later, instinctively move toward the brightest horizon, which under natural conditions is the moon and starlight reflecting off the ocean's surface. Without the moon, both nesting females and hatchlings would lose these critical navigational cues. Nesting might become less synchronized and potentially less successful as turtles struggle to identify optimal conditions. Hatchlings would face even greater challenges, as their evolutionary programming to move toward the brightest horizon would no longer reliably guide them to the ocean. For these ancient reptiles, already threatened by human activities, the loss of lunar guidance could represent yet another obstacle to survival. The moon's influence extends to terrestrial animals as well. Many species show subtle behavioral changes with the lunar cycle. Nocturnal mammals often modify their activity patterns based on moonlight levels, typically reducing movement during the brightest nights to avoid predation. Predators, conversely, may take advantage of moonlit nights to hunt more efficiently. Without the moon, these behavioral patterns would need to readjust, potentially altering predator-prey dynamics in many ecosystems. Some bird species use the moon as a navigational aid during migration, particularly those that travel at night. The precise mechanisms vary, but the moon provides both a light source and a reference point in the night sky. Its its absence would remove one tool from migratory birds' navigational toolkit, potentially making their journeys more challenging, especially when other cues like stars are obscured by clouds. Even primates, our closest relatives, show responses to lunar cycles. Some species of lemurs, for instance, show heightened activity and increased feeding during full moon nights, taking advantage of the improved visibility. Various monkey species also adjust their behavior based on moon phases. These patterns suggest that our own distant ancestors likely lived in rhythm with the lunar cycle as well, a connection that persists in human cultural practices around the world. The moon's influence on human biology remains a subject of scientific debate. While clear lunar effects have been documented in many animal species, the evidence for direct physiological effects in humans is more equivocal. Some studies suggest subtle correlations between the lunar cycle and sleep patterns, hormone levels, or even birth rates, but others find no significant relationships. What's clear, however, is that human societies throughout history have organized their activities partly in response to lunar cycles, creating cultural patterns that indirectly affect biological rhythms. Beyond reproduction and behavior, the moon has shaped evolution itself through its effects on Earth's environment. The stable axial tilt, maintained by the moon's gravitational influence, has created predictable seasonal patterns that have directed evolutionary adaptations for millions of years. Species have evolved precise timing for migration, hibernation, reproduction, and other critical life cycle events based on these reliable seasonal cues. In a world without the moon, where the axial tilt wobbled chaotically over time, these carefully evolved timing mechanisms would become maladaptive. Consider the precisely timed migrations of birds like the Arctic tern, which travels from pole to pole annually, or the extraordinary monarch butterfly, whose multi-generational migration spans North America. These journeys depend on the reliable progression of seasons. As seasons became increasingly unpredictable without the moon's stabilizing influence, such migrations would face mounting challenges. Plants, too, have evolved in response to the stable seasonal patterns partly maintained by the moon. Many species use photoperiod, the relative length of day and night, to determine when to flower, fruit, or shed leaves. These adaptations allow plants to time their reproductive efforts to favorable conditions and to prepare for hostile seasons. Without the moon, as Earth's axial tilt varied chaotically, these timing mechanisms would gradually lose their adaptive value. Plant communities would likely shift towards species with more flexible life history strategies, potentially reducing diversity and changing ecosystem structure. The tides, one of the moon's most visible influences on Earth, have shaped the evolution of countless coastal and marine organisms. Intertidal zones, those areas of shoreline alternately submerged and exposed by the tidal cycle, represent one of our planet's most dynamic habitats. Species that live here have evolved remarkable adaptations to survive both underwater and exposed to air within a single day. Consider the adaptations of intertidal algae and invertebrates, which must withstand desiccation, temperature fluctuations, changing salinity, and shifting predator communities as the tides move in and out. Or think of the feeding adaptations of shorebirds, whose bills are specialized to extract prey from tidal flats during low tide. These adaptations represent millions of years of evolutionary responses to the rhythm of lunar tides. Without the moon, and with tidal ranges reduced to about 30% of their current magnitude, these intertidal zones would contract dramatically. The broad expanses of tidal flats that currently support millions of shorebirds during migration would shrink or disappear. The distinctive bands of algae and invertebrates visible on rocky shores, each species adapted to a specific tidal height, would compress into narrower zones. Many specialized intertidal species might not survive this habitat contraction, leading to simplified coastal ecosystems with reduced biodiversity. Estuaries where rivers meet the sea would also change significantly with reduced tidal range. These productive ecosystems currently benefit from the twice-daily flushing and nutrient mixing provided by lunar tides. Without this tidal pulsing, estuaries would become more stagnant and potentially more vulnerable to pollution and algal blooms. The many fish species that use estuaries as nursery grounds might find these habitats less suitable, affecting marine food webs and fisheries. Even deep ocean ecosystems feel the moon's influence. The internal waves generated when tides move across underwater topography create mixing that brings nutrients from the deep ocean toward the surface, supporting productivity in otherwise nutrient-poor regions. Without the moon, this mixing would decrease, potentially reducing the productivity of fisheries in certain ocean regions. Bioluminescent organisms, those capable of producing their own light, often show relationships with lunar cycles. Many adjust their light production based on ambient light levels, producing less bioluminescence during the full moon to avoid attracting predators or to save energy when communication through light is less effective against the brighter background. Without moonlight, these organisms would need to adjust their light production strategies, potentially changing the patterns of light in the deep ocean and the communication networks that depend on them. For humans, the biological consequences of losing the moon would initially be less severe than for many other species, thanks to our remarkable adaptability and technological buffering. Yet even our biology has been shaped by life on a moon-influenced Earth. Our visual systems evolved partly in response to the levels of light experienced on our planet, including moonlight. Our sleep-wake cycles developed in the context of predictable day-night patterns stabilized by lunar tidal breaking. While we might adapt to the moon's absence through cultural and technological means, our bodies would still register the change at some level. As complex ecosystems began to respond to the moon's absence, humans would experience secondary effects through our dependence on ecosystem services. Fisheries would be affected by changes in marine reproduction, estuarine productivity, and ocean mixing. Agricultural systems might face new challenges from shifts in pollinator behavior or changed seasonal patterns. Even human disease patterns might shift as vector species like mosquitoes adjusted their breeding cycles previously influenced by lunar rhythms. The disappearance of the moon would not trigger an immediate biological catastrophe. Rather, it would set in motion a gradual unraveling of countless evolutionary adaptations that have developed in response to the stable conditions the moon has helped maintain. Some species would adapt successfully to the new conditions. Others would decline or face extinction. The overall pattern would likely be one of simplification, with diverse, specialized communities gradually replaced by more homogeneous assemblages of adaptable generalist species. This simplification would happen unevenly across Earth. Some ecosystems would prove more resilient than others. Tropical rainforests, with their high diversity and relatively stable local climates, might initially show more resistance to change. Polar and high-altitude ecosystems, already adapted to extreme conditions, might experience more immediate disruption as seasonal patterns shifted. Coastal systems would transform most visibly as the tidal range decreased. Over longer timescales, as Earth's axial tilt began its chaotic wobble, even the most resilient ecosystems would face mounting challenges. Plants and animals have responded to past climate changes by shifting their ranges, moving toward conditions that match their adaptations. But the chaotic climate patterns that would eventually develop on a moonless Earth would create a more challenging situation, with no clear geographic refuge for many specialized species. The species most likely to thrive in this new world would share certain characteristics. Short generation times would allow for more rapid evolutionary adaptation. Phenotypic plasticity, the ability to adjust development and physiology in response to environmental conditions, would become increasingly valuable. Generalist feeding and habitat requirements would provide more options as ecosystems transformed. Effective dispersal mechanisms would allow organisms to track suitable conditions as they shifted unpredictably across the landscape. We can look to certain modern species as examples of the types of organisms that might fare relatively well. Cockroaches, with their flexible diet, rapid reproduction, and tolerance for varying conditions, embody the kind of adaptability that would be advantageous. Among plants, those with efficient seed dispersal mechanisms and the ability to remain dormant until conditions become favorable, like many desert species, might have advantages. In the oceans, jellyfish, with their simple body plans and opportunistic feeding, might become increasingly dominant. This is not to suggest that all complex or specialized organisms would disappear. Evolution has produced remarkable adaptations to extreme and variable conditions before. New specializations would eventually emerge, adapted to whatever patterns could be found in the new, more chaotic Earth system. But the transition would likely involve substantial biodiversity loss and ecosystem simplification. For a perspective on how life responds to the moon's influence, we can look to natural experiments in the form of underground ecosystems. Deep caves provide environments permanently shielded from both sunlight and moonlight, where lunar cycles have no direct influence. Life in these settings has evolved in the absence of lunar cues, developing alternative timing mechanisms based on other environmental factors. Cave-adapted fish, for instance, have lost the lunar influence spawning synchronization seen in their surface relatives, instead breeding year-round or responding to subtle cues like flooding events. Similarly, deep-sea environments experience little direct lunar influence beyond the internal waves and mixing mentioned earlier. Organisms in these settings have evolved timing mechanisms independent of lunar cycles, often based on internal clocks or responses to local environmental changes, rather than celestial cues. These examples suggest that life can indeed adapt to the absence of lunar influences, though such adaptations typically develop over many generations. A particularly interesting case study comes from lake ecosystems, where tides are minimal or non-existent, but moonlight still penetrates. Here, some species show lunar synchronized behaviors despite the absence of significant tidal cues, suggesting that light alone can serve as an important timing mechanism. This observation gives us clues about which types of lunar influence behaviors might persist through other mechanisms after the moon's disappearance, and which might be lost entirely. As we contemplate these biological changes, it's worth considering the philosophical implications of losing a celestial body that has influenced life for billions of years. The moon has been present throughout the evolution of life on Earth, a constant companion as simple single-celled organisms evolved into the complex diversity we see today. Its rhythms have become integrated into the very fabric of life, from cellular processes to ecosystem dynamics. In many ways, life on Earth has evolved not just in response to the planet itself, but to the Earth-Moon system as a whole. The disappearance of the moon would therefore represent not just the loss of a beautiful object in our night sky, but the disruption of a cosmic relationship that has shaped the development of life from its earliest beginnings. For the countless species whose biology is intimately tied to lunar cycles, the moon isn't merely an external influence but an integral part of their evolutionary history, their physiology, and their behavioral programming. Its absence would create a void not easily filled, a missing rhythm in the cosmic symphony to which life has been dancing for eons. Human appreciation for biodiversity would take on new dimensions in this scenario, as we witness the gradual transformation of ecosystems in response to the moon's absence. We might develop a deeper understanding of the complex interconnections between Earth, Moon, and the rich tapestry of life they jointly support. The corals spawning in magical synchrony, the sea turtles navigating by moonlight, the intertidal communities adapted to the rhythm of lunar tides, all would stand revealed as expressions of a cosmic relationship far older than humanity itself. This understanding might in turn inspire greater humility and care in our own relationship with Earth's living systems. Recognizing the profound vulnerability of life to cosmic changes beyond our control might encourage us to minimize the disruptions within our control, preserving as much as possible of the extraordinary biological heritage shaped by billions of years of evolution on a moon-influenced Earth. As we continue our exploration of a moonless Earth, we carry with us this appreciation for the moon's biological legacy. Life dances to the moon's rhythm. Without it, some songs may go silent, but life in its remarkable adaptability, would continue its dance, finding new rhythms in the changed conditions of a moonless world. Without moonlight, darkness becomes deeper and the night more mysterious. We take for granted the silver glow that bathes our world on clear nights when the moon rides high. This gentle illumination, neither as harsh as daylight nor as complete as true darkness, creates a twilight realm that has shaped not only the evolution of countless species, but also human culture, navigation, and our very perception of the night. If the moon were to vanish, one of the most immediate and palpable changes would be the newfound darkness of our nights. The full moon on a clear night provides approximately 0.1 to 0.3 lux of illumination, about 1/1,000,000th the brightness of direct sunlight. While this may seem faint compared to daylight or artificial lighting, it represents a significant source of natural nighttime illumination. On a moonlit night, human eyes can discern shapes, movement, and even some colors. We can navigate familiar landscapes without artificial light, distinguish friend from foe at moderate distances, and perform simple tasks outdoors. Without the moon, nights would be illuminated only by starlight, airglow, and occasionally the aurora. Starlight provides approximately 0.000 lux, hundreds of times dimmer than moonlight. In this profound darkness, human vision would be severely limited. Colors would disappear entirely, replaced by shades of grey, perceived only by the rod cells in our retinas. Forms would blur into shadows, and navigation across even familiar terrain would become challenging. The simple act of walking through a forest or along a mountain path, easily accomplished under moonlight, would become treacherous in the deep darkness of a moonless world. For most of human history, before the advent of widespread artificial lighting, moonlight played a crucial role in extending human activity beyond daylight hours. Ancient civilizations planned travel, military operations, and agricultural activities around the lunar phases. Religious ceremonies and cultural gatherings were often timed to coincide with the full moon, taking advantage of its illumination. Without the moon, these nighttime activities would have been severely curtailed, potentially altering the course of human cultural development. Navigation, in particular, would have faced greater challenges in a moonless world. From prehistoric times until the recent development of electronic navigation systems, moonlight provided crucial visibility for travelers moving at night, whether on land or sea. Sailors used the moon not only for illumination, but also as a navigational reference, observing its position and phase to help determine location and time. Without these lunar cues, nighttime navigation would have relied more heavily on stars alone, a significantly more challenging prospect, especially under partly cloudy conditions when only portions of the star field might be visible. Even in our modern world of artificial lighting and GPS systems, the absence of moonlight would be keenly felt. Many remote or underdeveloped regions still rely on moonlight for nighttime activities. Rural communities without extensive electrical infrastructure often time outdoor evening work and social gatherings around the lunar calendar. The loss of moonlight would impose new limitations on these communities, potentially increasing dependency on artificial lighting and the energy resources it requires. For nocturnal animals, the disappearance of moonlight would represent a significant environmental change, triggering cascading effects through ecosystems worldwide. Many species have evolved precisely calibrated responses to varying levels of moonlight, creating a complex tapestry of behaviors that would be disrupted in a moonless world. Consider the intricate predator-prey dynamics that have evolved around moonlight. Many small mammals reduce their activity during brighter nights, seeking the safety of cover to avoid being spotted by predators. Owls and other visual predators, conversely, often hunt more efficiently under moonlight, using the improved visibility to locate prey. Without the moon, these behavioral patterns would need to recalibrate, potentially shifting the balance between predator and prey species in many ecosystems. Some animals have evolved to take specific advantage of moonlight. Scorpions, for instance, glow under ultraviolet light, including the UV component of moonlight, due to compounds in their exoskeletons. This fluorescence may serve communication functions or help them gauge light levels to avoid predators. Without moonlight, this adaptation would lose its utility, becoming an evolutionary vestige. For visual creatures that have specialized in nighttime activity, the darkness of a moonless world might initially seem advantageous, offering greater concealment. However, many nocturnal hunters depend on at least minimal light for effective hunting. Great horned owls and other raptors with exceptional night vision actually hunt more successfully under moderate moonlight than in complete darkness. The elimination of moonlight might paradoxically disadvantage some nocturnal predators, forcing adaptations in hunting strategies or activity patterns. The night sky itself would be transformed without the moon. On one hand, the absence of moonlight would reveal a far more star-filled sky than most modern humans ever experience. Without lunar light washing out the fainter stars, the Milky Way would appear more brilliant and detailed, and thousands of stars, invisible under even moderate moonlight, would emerge from the darkness. For astronomers, every night would offer the dark sky conditions currently available only during the new moon phase. Yet something profound would be lost as well. The moon is the only celestial object that reveals detailed structure to the naked human eye. Through even modest binoculars or small telescopes, its craters, mountains, and plains become a fascinating landscape in the sky, igniting curiosity about the cosmos in countless observers throughout history. The inspiration provided by this accessible astronomical spectacle has launched many careers in science and fueled human imagination for millennia. Without the moon, our cosmic perspective would be simultaneously more expansive in its view of the deeper universe and more limited in its tangible connection to our nearest celestial neighbor. The psychological impact of moonless nights should not be underestimated. Humans have evolved under cyclic lunar illumination, and the moon has informed our art, mythology, literature, and emotional connections to the night for as long as we have been human. There is something fundamentally reassuring about the moon's presence, a familiar face in the darkness that connects us to our ancestors who gazed upon the same celestial body thousands of years ago. In many cultures, the moon has been associated with protection, guidance, and illumination in both the literal and metaphorical sense. Its regular phases provide a sense of cosmic order and predictability. Without this comforting presence, might humans experience the night as more threatening, more alien? Would we retreat further from the natural darkness, increasing our already substantial reliance on artificial lighting? The emotional and cultural dimensions of losing moonlight might prove as significant as the practical challenges of navigating darker nights. Indeed, artificial lighting would likely increase in a moonless world, particularly in regions currently accustomed to sufficient moonlight for basic nighttime activities. This increased lighting would bring its own consequences, potentially worsening light pollution that already affects urban and suburban areas. Greater artificial illumination would further disrupt the circadian rhythms of plants and animals, exacerbating a problem already significant in many ecosystems. For plants, the absence of moonlight might have subtle but important effects. While most plants conduct photosynthesis primarily under sunlight, research has shown that some species can actually perceive and respond to moonlight. Certain plants time their flowering based partly on lunar illumination, and some even demonstrate different opening patterns of leaves or flowers under moonlight compared to complete darkness. These lunar responsive behaviors would become obsolete in a moonless world, representing yet another subtle environmental cue lost to the planetary ecology. Perhaps most affected by the loss of moonlight would be the many marine species that rely on light levels to guide their vertical migrations. Many zooplankton and fish move toward the surface at night to feed, then descend to darker depths during daylight to avoid predators. Research has shown that these migrations are often modulated by moonlight, with many species staying deeper on brightly moonlit nights. Without lunar illumination, these migration patterns would simplify to a day-night rhythm, potentially altering predator-prey interactions and nutrient cycling in marine ecosystems. For humans living in polar regions, the absence of moonlight would be particularly impactful. During the long polar night, when the sun remains below the horizon for months, moonlight currently provides crucial illumination. The full moon in Arctic or Antarctic winter creates a beautiful and functional twilight landscape that breaks the otherwise constant darkness. Without this periodic relief, polar winters would become even more psychologically challenging for human inhabitants and more physically challenging for Arctic wildlife that uses the moonlit periods for feeding and other essential activities. Consider the traditional knowledge of indigenous Arctic peoples, who have developed sophisticated understanding of how the moon's path and phases affect their environment. The Inuit, for instance, have specific terms for different types of moonlight conditions and their effects on hunting, travel, and natural phenomena. This rich body of knowledge, accumulated over countless generations, would become a cultural relic in a moonless world, no longer applicable to daily life, yet testifying to the deep connection between human culture and the cosmos. Throughout history, moonlight has influenced human creativity and expression. Artists have long been captivated by the unique quality of lunar illumination, with its silvery glow that transforms familiar landscapes into mysterious realms. From classical Chinese poetry to European romantic painting to contemporary photography, moonlight has provided both subject matter and lighting conditions that spark artistic innovation. Without the moon, this particular muse and medium would be lost to human creativity. The absence of moonlight would also change our relationship to darkness itself. In our increasingly illuminated world, true darkness has become rare, with artificial lighting creating a perpetual twilight in populated areas. Natural moonlight, as the primary nocturnal illumination throughout human evolution, represents an intermediate light level to which our visual and psychological systems are well adapted. Without this familiar middle ground between bright light and complete darkness, our experience of night would become more binary, potentially altering how we perceive, navigate, and emotionally respond to the hours of darkness. For children growing up in a moonless world, the night might hold different meanings than it has for countless generations before them. The gradual introduction to darkness provided by moonlight, neither as overwhelming as complete night nor as revealing as day, has helped young humans develop comfort with the night. Would children in a moonless world develop different relationships with darkness? Would they miss the gentle entry point to night that the moon has traditionally provided? Or would they simply adapt, their neural pathways and emotional responses calibrated to a different range of natural light conditions? Security and safety considerations would also change in a world without moonlight. Throughout history, military planners have factored lunar phases into their strategic thinking, with full moon periods offering better visibility for movement and operations, but also increasing vulnerability to detection. Without the moon, nighttime would offer more consistent concealment, potentially changing tactical and strategic approaches to security. For civilian safety, darker nights might increase accidents and crime in areas without artificial lighting, creating new challenges for public safety planning. Perhaps most profoundly, the absence of moonlight would alter our connection to the cosmic environment. The moon is our celestial companion, the only other world whose surface features are readily visible to the naked eye. Its changing phases and passage through our sky create a tangible link to the universe beyond Earth, a constant reminder that we inhabit one body among many in a vast cosmos. Without this visible companion, might our gaze turn more exclusively earthward? Would our innate human curiosity about the universe find different expression, or might it somewhat diminish without the moon's nightly invitation to look up and wonder? As we contemplate these changes, we should remember that humans are remarkably adaptable. We would certainly adjust to moonless nights, developing new customs, technologies, and relationships with darkness. Yet something profound would be lost. A quality of light and shadow that has shaped our evolution, our cultures, and our psychological relationship with the night sky for as long as our species has existed. Without moonlight, darkness becomes deeper, and the night more mysterious. The familiar silver path across lake waters, the comforting glow that turns familiar landscapes into dreamscapes, the gentle illumination that has guided countless travelers through the darkness, all would vanish, leaving us to navigate a night more absolute in its darkness, more unfamiliar in its aspect, more challenging in its obscurity. And in that deeper darkness, we might come to appreciate just how much the moon's gentle light has shaped our world and our experience of the night. When the moon disappears, it leaves behind not just tides, but meaning. The moon has been humanity's constant companion, not just physically, but spiritually and culturally. Since our earliest ancestors first gazed skyward, this luminous orb has inspired wonder, awe, and meaning-making across every human civilization. The moon has been woven into our mythologies, our religions, our art, our literature, our calendars, and our understanding of ourselves. If it were to vanish, we would lose not just a celestial body, but a universal cultural touchstone that has helped define humanity's place in the cosmos for thousands of generations. Perhaps the most fundamental cultural role of the moon has been as a timekeeper. Long before written language or formal astronomy, humans recognized the moon's regular cycle of phases. This approximately 29.5-day period, from one full moon to the next, became one of the first reliable ways to track time beyond the day-night cycle. The very concept of a month derives from the moon's phases, with the word month sharing etymological roots with moon in many languages. Ancient calendars worldwide were predominantly lunar or lunisolar, organizing human activities around the predictable rhythm of the moon's appearance. Agricultural planting and harvesting, religious observances, community gatherings, and even military campaigns were timed to lunar phases. The Islamic calendar remains lunar to this day, with months beginning at the first sighting of the crescent moon. Jewish, Hindu, Buddhist, and Chinese calendars, among others, still incorporate lunar cycles in determining dates for important holidays and observances. Without the moon, these lunar-based timekeeping systems would lose their reference point. Cultures would need to reorganize their calendars solely around the solar year and its seasons, losing the intuitive connection to a visible celestial cycle that even the most ordinary person could observe and track. The measurement of time, that most fundamental organization of human experience, would become more abstract and less connected to direct observation of the natural world. Beyond practical timekeeping, the moon has featured prominently in the mythologies and religious traditions of virtually every human culture throughout history. These lunar deities and myths reveal our ancestors' attempts to understand the cosmos and humanity's place within it. Across extraordinarily diverse cultures, certain themes recur in lunar mythology, including cycles of death and rebirth, feminine energy, and the governance of waters and fertility. In ancient Egypt, the lunar deity Khonsu governed time and fertility. The Greeks associated the moon with Artemis and later Selene, while the Romans worshipped Luna. In Hindu tradition, Chandra rides his chariot across the night sky, while in Chinese mythology, Chang'e resides in the moon palace. Japanese Shinto traditions honor Tsukuyomi, god of the moon, while many indigenous American mythologies feature lunar deities governing tides, fertility, and time. These divine associations reflect humanity's consistent tendency to find meaning and agency in the night sky. The moon, with its changing yet predictable face, inspired stories that helped explain natural phenomena while embedding cosmic cycles into cultural understanding. Without the moon, these mythological systems would become historical artifacts rather than living traditions connected to observable celestial patterns. The moon's phases have also served as powerful metaphors across human cultures. The cycle from new moon to full and back again has symbolized the circle of life, death, and rebirth. The waxing and waning of fortune, the rhythms of feminine energy, and countless other cyclical aspects of existence. Literature, poetry, religious texts, and oral traditions worldwide draw on lunar imagery to convey deeper truths about the human condition. Consider how Shakespeare alone used the moon as metaphor in his works. The moon's an arrant thief, and her pale fire she snatches from the sun. Timon of Athens, how sweet the moonlight sleeps upon this bank. The merchant of Venice, it is the very error of the moon. She comes more nearer earth than she was wont, and makes men mad. Othello, the moon provided a universally recognized reference point for describing beauty, inconstancy, madness, romance, and transformation. Without the moon, literature would lose one of its most potent and universal symbols. Future poets and storytellers could reference the moon only historically, creating an inevitable disconnect between ancient texts and the lived experience of their readers. The emotional resonance of lunar imagery would gradually fade as generations grew up without witnessing the moon's gentle light or its mysterious transformations. Visual arts would similarly lose a subject that has inspired countless works spanning millennia, from prehistoric lunar calendars carved into bone and stone to Chinese and Japanese ink paintings. From romantic European landscapes to contemporary photography, artists have been captivated by the moon's visual drama and symbolic power. The soft, directional illumination of moonlight creates a distinctive aesthetic experience that has motivated artistic creation across cultures and eras. Consider the technical and aesthetic challenges the moon has presented to visual artists, capturing its luminous quality against the dark sky, representing its detailed surface features, depicting its reflection on water, or its illumination of landscape. All require careful observation and technical skill. Without the moon as subject and light source, entire artistic traditions would lose their foundation. Future artists might study historical lunar representations without the ability to connect them to direct experience. Musical traditions worldwide also reference the moon, from classical compositions like Debussy's Clair de Lune and Beethoven's Moonlight Sonata to countless folk songs, ballads, and contemporary pieces. The moon's associations with romance, mystery, longing, and transcendence have made it an enduring motif in musical expression across genres and cultures. Without the moon, these compositions would become increasingly abstract references to an absent celestial body rather than evocations of a shared visual and emotional experience. The moon has been particularly significant in romantic traditions across cultures. Lovers meeting by moonlight is a ubiquitous motif, from ancient poetry to modern film. The moon's soft illumination creates an atmosphere between concealment and revelation, privacy and visibility that seems uniquely suited to romantic encounters. Its beauty inspires declarations of love, with countless couples across history making promises by the light of the silvery moon. Without lunar light, future generations would need to find new natural phenomena to inspire and witness their romantic sentiments. Many cultures have also associated the moon with fertility, both human and agricultural. Planting by the lunar calendar remains a practice among traditional farmers worldwide, based on observations of how lunar phases appear to influence plant growth, moisture retention, and pest activity. The approximate alignment of the lunar cycle with the human menstrual cycle has reinforced associations between the moon and female fertility across diverse cultural traditions. Without the moon, these associations would lose their observational basis, becoming cultural memories rather than living connections between human experience and cosmic cycles. Beyond romantic and fertility associations, the moon has represented psychological states across cultural traditions. Lunacy, derived directly from Luna, the Roman moon goddess, reflects ancient beliefs that the full moon could induce mental instability. The concept of the werewolf, a human transformed into a wolf during the full moon, appears in various forms across many cultures, symbolizing the thin line between civilization and wildness, reason and instinct. These motifs have informed literature, film, and popular culture for centuries, creating a rich symbolic vocabulary that would lose its immediate relevance without the moon's presence. Particularly significant would be the loss of the moon as a unifying cultural reference point. Throughout human history, despite vast differences in language, religion, and social organization, people everywhere have shared the experience of gazing at the same moon. This celestial body has served as a reminder of our common humanity and shared planet in a way that transcends cultural differences. When Neil Armstrong and Buzz Aldrin walked on the lunar surface in 1969, an estimated 600 million people, 1/5 of humanity at the time, watched the broadcast, making it one of the most unifying events in human history. Without the moon, future generations would lose this universal reference point. While the sun, stars, and planets would remain, none provides the same combination of visibility, distinctive appearance, and changing yet predictable behavior that has made the moon such a powerful cross-cultural symbol. The night sky would become more homogeneous, lacking its most distinctive feature, the one celestial body close enough to reveal topographic details to the naked eye. For indigenous and traditional cultures that have maintained strong connections to lunar cycles, the moon's disappearance would represent a particularly profound loss. Many indigenous knowledge systems incorporate detailed understanding of lunar influences on tides, animal behavior, plant growth, and other natural phenomena. These knowledge traditions, developed over countless generations of careful observation, would lose their immediate application, becoming historical rather than living wisdom. Consider the moon counting traditions of the Maori of New Zealand, who developed an intricate naming system for each night of the lunar cycle, with specific associations for fishing, planting, and harvesting activities, or the sophisticated lunar calendars of Maya civilization, which integrated astronomical observation with agricultural and religious practices. These knowledge systems represent not just practical tools, but core elements of cultural identity and relationship with the natural world. Their disruption would further challenge the continuity of traditional ways of life already under pressure from modernization. The moon has also played a significant role in the development of science and human understanding of the cosmos. Galileo's observations of lunar mountains and craters in 1609 provided some of the first evidence that celestial bodies were physical worlds, rather than perfect divine spheres, helping to launch the scientific revolution. Tracking the moon's orbit helped Isaac Newton develop his theory of universal gravitation. In more recent times, the Apollo missions to the moon represented a pinnacle of human technological achievement, while providing valuable scientific insights into the formation of the Earth-Moon system and the early solar system. Without the moon as an accessible target for observation and exploration, the development of astronomy and space science might have followed a different trajectory. The moon has served as a stepping stone for human understanding, more distant and challenging than Earth, but more accessible than other planets. Its disappearance would remove this natural first destination for space exploration, potentially altering humanity's path to becoming a spacefaring civilization. Perhaps most fundamentally, the moon has helped human cultures orient themselves cosmically. As our nearest celestial neighbor, visibly changing yet permanently present, the moon has served as a mediating presence between the terrestrial and the cosmic. Its cycles have connected daily human experience to larger patterns of time and space, helping cultures worldwide develop cosmologies that place human existence within a comprehensible universal order. Without the moon, the conceptual distance between Earth and the rest of the cosmos would increase. The night sky would still contain the sun, planets, and stars, but these either appear as mere points of light, stars and planets, or are present only during the day, the sun. The moon's disappearance would remove the one celestial body that appears as a detailed world in our sky, visibly different from Earth, yet clearly part of the same cosmic system. This loss might subtly shift human perception toward a greater sense of isolation in the universe. For future generations born into a moonless world, these cultural losses would not be experienced as active grief, but rather as a kind of cosmic impoverishment, an absence they might not fully comprehend. They would study lunar mythology and moon-inspired art, as we might study ancient religious practices based on deities no longer worshipped. They would read lunar metaphors in historical literature, without the immediate emotional resonance that comes from personal experience. They would learn about the moon through images and descriptions rather than direct observation. Educational approaches would necessarily change. Astronomy lessons would rely entirely on photographs and simulations, rather than encouraging students to observe lunar features with the naked eye or simple telescopes. Cultural histories would need to explain the pervasive influence of an absent celestial body on human artistic and religious traditions. The visceral connection between cultural expressions and natural phenomena would be weakened, creating a more abstract relationship between human meaning-making and the observable universe. Some communities might develop commemoration practices to maintain cultural memory of the moon. Annual observations might mark the anniversary of its disappearance, keeping alive stories of how it appeared in the sky and influenced life on Earth. These practices might resemble how some traditional cultures maintain memories of sacred places or species lost to environmental change, attempting to preserve knowledge that future generations cannot directly experience. New cultural expressions would eventually emerge in response to the moonless sky. Just as ancient cultures created myths to explain the moon's presence and behavior, future generations might develop stories to explain its absence. Art, literature, and music would find new cosmic references and metaphors. Human creativity would adapt to the changed celestial environment, perhaps finding new meaning in the starry sky newly visible without lunar light, or in other natural phenomena that took on greater significance in the moon's absence. Yet there would remain a gap in human experience, a missing reference point that had helped orient countless generations. The moon has been witness to the entire human story, from our earliest ancestors to modern civilization. Its disappearance would sever a connection that has persisted throughout human evolution and cultural development, a constant presence that has illuminated not just our nights, but our understanding of ourselves as terrestrial beings with cosmic awarenesses. For all our technological advancement and cultural complexity, humans remain responsive to natural cycles and patterns. The moon's rhythm has been internalized in our cultural consciousness over thousands of years. Its absence would create a void not easily filled by artificial substitutes. We would continue to create meaning and measure time, but something profound would be lost. A cosmic relationship that helped define what it means to be human on this particular planet. When the moon disappears, it leaves behind not just tides, but meaning. The loss would extend beyond physical consequences to the very foundations of human culture and self-understanding. The myths, art, music, literature, and science inspired by our celestial companion would become historical artifacts rather than living traditions connected to observable reality. And in this subtle yet pervasive way, human experience would be diminished, our relationship with the cosmos altered in ways that might be felt, but not fully articulated by generations who never witnessed the silver light of the full moon, transforming an ordinary landscape into a realm of mystery and possibility. The absence of the moon echoes even in our ambitions to leave Earth. Beyond its effects on Earth's physical systems and cultural traditions, the moon's disappearance would profoundly impact humanity's scientific understanding and space exploration capabilities. As our nearest celestial neighbor, the moon has served as both laboratory and launchpad for our cosmic ambitions. Its absence would alter not just our view of the night sky, but our pathway to becoming a spacefaring civilization. The moon has been humanity's natural first step into the cosmos. At an average distance of 384,000 kilometers, it represents a challenging yet achievable destination, allowing us to develop and test space technologies without immediately confronting the far greater distances to other planets. The Apollo missions of the 1960s and 70s, which remain humanity's only ventures beyond low Earth orbit, demonstrated our capacity to reach another world while establishing technical and operational knowledge that continues to inform space exploration. Without the moon as an initial target, the progression of human space exploration would likely follow a different trajectory. The leap from Earth orbit to Mars or Venus would represent a much more dramatic technological and logistical challenge without the intervening step of lunar missions. The absence of the moon might slow humanity's outward expansion, requiring more substantial advances before attempting missions to other planetary bodies. Current plans for space development heavily feature the Moon as a proving ground and eventual outpost. Space agencies worldwide have announced intentions to establish lunar bases in the coming decades, using them to develop technologies and operational experience for eventual Mars missions. The lunar surface offers valuable resources, including water ice at the poles that could be processed into rocket fuel and life support supplies. These moon-based resources could significantly reduce the mass that needs to be launched from Earth for deep space missions, potentially making such ventures more economically viable. In a moonless scenario, these plans would require complete reconsideration. Mars would likely become the default next destination, but reaching the red planet requires a journey of at least 6 months with current propulsion technology, compared to just 3 days to the Moon. The psychological, physiological, and engineering challenges of such extended missions would need to be addressed without the benefit of prior experience on shorter lunar expeditions. The development of space exploration capabilities would potentially progress more slowly and at greater cost, without the relatively accessible lunar testing ground. Even more significantly, the Moon's absence would affect the orbital mechanics of spaceflight beyond Earth. The Moon's gravitational field currently enables mission planners to use lunar gravity assists, where a spacecraft flies past the Moon to gain velocity without expending fuel. This technique has been crucial for many interplanetary missions. Without the Moon, these trajectories would be unavailable, requiring more propellant or longer transit times for missions to the outer solar system. The Earth-Moon Lagrange points, positions in space where the gravitational forces of the two bodies and the centrifugal force balance to create stable or semi-stable locations for spacecraft, would also disappear. These points, particularly L1 and L2, are valuable locations for space observatories and communication relays. The James Webb Space Telescope, for instance, orbits around the Earth-Moon L2 point. Without the Moon, these gravitationally advantageous positions would no longer exist, eliminating potential locations for future scientific instruments and infrastructure. The scientific loss would extend beyond practical spaceflight considerations. The Moon has served as an invaluable record keeper of solar system history. Unlike Earth, which has undergone constant geological recycling through plate tectonics, weathering, and erosion, the Moon has preserved its surface features for billions of years. Its cratered face tells the story of the late heavy bombardment and other major events in solar system evolution. Without the Moon, scientists would lose access to this crucial historical record, making it more difficult to reconstruct the early history of our solar system. Lunar samples returned by Apollo astronauts and robotic missions have provided irreplaceable scientific insights. Analysis of moon rocks has helped establish the giant impact theory of lunar formation, improved our understanding of the solar system's chronology, and revealed details about the early Earth that have been erased from our own planet's geological record. The Moon essentially serves as a preserved snapshot of conditions from the early solar system. Its disappearance would eliminate this scientific resource, leaving significant gaps in our understanding of planetary formation and evolution. The Moon also serves as a natural laboratory for studying astronomical phenomena. Its lack of atmosphere makes it an ideal platform for astronomical observations, free from the distortion, light pollution, and limited wavelength transmission that affect Earth-based telescopes. Future lunar observatories have been proposed that would offer unprecedented views of the universe. Without the Moon, astronomers would need to rely more heavily on space-based telescopes or develop alternative approaches for achieving similar observational capabilities. For planetary science, the Moon offers a valuable comparison point to Earth, helping scientists understand what makes our planet unique and habitable. By studying these two worlds that formed from similar material but followed different evolutionary paths, researchers gain insights into the factors that influence planetary development. The Moon's absence would remove this crucial comparative case, potentially limiting our understanding of Earth's exceptional characteristics. In the field of astrobiology, the search for life beyond Earth, the Moon plays a more subtle but still significant role. While the moon itself is not considered a potential habitat for life, understanding the Earth-Moon system helps scientists identify the conditions that make a planet habitable. The moon's stabilizing effect on Earth's axial tilt, its influence on tidal pools that may have facilitated life's early development, and its role in Earth's long-term climate stability all inform models of habitability for exoplanets. Without the moon as a case study, astrobiologists would have a less complete understanding of the factors that contribute to a planet's life-supporting capacity. Space weather monitoring would also be affected by the moon's absence. The moon serves as a natural shield when it passes between Earth and the Sun, occasionally blocking solar outbursts from reaching our planet. More importantly, instruments on the lunar surface or in lunar orbit provide valuable data points for studying solar activity and its effects on the space environment. Without these capabilities, our ability to predict and mitigate the impacts of solar storms on satellites, power grids, and other infrastructure might be reduced. From a technological perspective, the moon has inspired the development of numerous innovations that have applications both in space and on Earth. Technologies created for lunar exploration, from the original Apollo program to more recent robotic missions, have led to advances in materials science, computing, telecommunications, and numerous other fields. Without the moon as a driver for these developments, technological progress might follow different paths, potentially missing innovations that would have emerged from lunar-focused research and development. The moon also represents a potential future source of resources that could benefit Earth and space development. Lunar regolith contains oxygen, silicon, aluminum, iron, titanium, and other useful elements. Helium-3, deposited on the lunar surface by the solar wind, has been proposed as a potential fuel for future fusion reactors. Water ice at the lunar poles could provide not just drinking water and breathable oxygen for astronauts, but also hydrogen and oxygen for rocket propellant. In a moonless scenario, these resources would be unavailable, potentially limiting options for sustainable space development and beneficial technologies on Earth. Earth observation would be another scientific area affected by the moon's absence. Instruments on the lunar surface or in lunar orbit provide unique vantage points for monitoring Earth systems. From this perspective, scientists can observe large-scale climate patterns, track changes in ice coverage, monitor atmospheric composition, and study other important environmental indicators. While satellites in Earth orbit provide similar capabilities, lunar-based observations offer complementary data from a different perspective and distance. Without these observation points, our ability to monitor and understand Earth's complex systems might be somewhat diminished. For planetary defense, the effort to protect Earth from potential asteroid or comet impacts, the moon serves both as a natural shield and as a potential base for detection and deflection systems. The moon absorbs some impacts that might otherwise reach Earth, as evidenced by its heavily cratered surface. Future planetary defense systems might use lunar-based telescopes and spacecraft to provide early warning and response capabilities. Without the moon, Earth would face a slightly increased impact risk, while losing a potential platform for protective measures. The absence of the moon would also alter our understanding of fundamental physics. The Earth-Moon system has allowed scientists to test theories of gravity with high precision. Lunar laser ranging experiments, which measure the exact distance to the moon by timing how long laser pulses take to reflect off retroreflectors placed on the lunar surface by Apollo astronauts, have provided some of the most stringent tests of Einstein's theory of general relativity. Without the moon as a testing ground, certain aspects of gravitational physics might remain less thoroughly verified. Beyond these practical and scientific considerations, the moon's absence would affect the psychological and philosophical dimensions of space exploration. As a visible, attainable destination in our sky, the moon has served as an aspirational target for humanity, a symbol of our ability to reach beyond our home planet. The famous Earthrise photograph taken during the Apollo 8 mission, showing our blue planet rising above the lunar horizon, became an iconic image that transformed human perspective, highlighting both Earth's beauty and its isolation in space. Without the moon as a stepping stone, would humanity's outward urge be diminished? Would we still develop the same cosmic ambitions without this constant reminder of another world within our reach? These questions touch on the deeper motivations that drive space exploration beyond practical benefits or scientific knowledge. The moon has served as a kind of psychological bridge between the terrestrial and the cosmic, making the vast universe seem less impossibly distant. Its absence might subtly shift our relationship with space itself. For the generations who would grow up without ever seeing the moon in the sky, space might seem more abstract and less accessible. The visceral experience of looking up at another world visible to the naked eye would be lost, replaced by points of light or images on screens. While Mars and Venus are visible to the unaided eye, they appear only as bright stars, not as worlds with discernible features. This change in immediate cosmic experience might influence the cultural and psychological foundations of space exploration in ways difficult to fully anticipate. Education in astronomy and planetary science would necessarily adapt to a moonless reality. Students would learn about the moon through historical records, photographs, and simulations rather than through direct observation. The hands-on experience of observing lunar features through basic telescopes, often an entry point into astronomy for young people, would no longer be available. Educational approaches would need to find new ways to create the same sense of wonder and connection that lunar observation has traditionally provided. Space agencies and private space companies would need to revise their long-term strategic plans in a post-moon scenario. Current roadmaps for human space exploration heavily feature lunar missions as precursors to Mars expeditions and deeper space ventures. Without the moon, these organizations would need to reconsider their incremental approach, potentially focusing more resources on developing technologies specifically for direct Mars missions, or establishing alternative stepping stones, such as extended stays at Lagrange points or near-Earth asteroids. The economics of space development would also shift. The moon represents a potential economic development zone, with possibilities for resource utilization, tourism, and scientific research. Various nations and companies have announced intentions to participate in lunar development in the coming decades. Without the moon, these economic opportunities would disappear, potentially slowing private investment in space capabilities or redirecting it toward different destinations and applications. Perhaps most profoundly, the absence of the moon would eliminate what might otherwise become humanity's first permanent foothold beyond Earth. The moon, with its proximity and useful resources, represents the most feasible location for establishing a self-sustaining human presence off Earth. While Mars and other destinations might eventually host human outposts, the moon offers a unique combination of accessibility and utility that makes it the natural first site for expanding human civilization beyond our home planet. Without this stepping stone, the timeline for becoming a multiplanetary species would likely extend further into the future. As we reflect on these scientific and exploratory implications, we recognize that the moon has been not just an object of study, but a partner in humanity's cosmic journey. Its presence has shaped our understanding of the solar system, our technological development, and our aspirations to reach beyond Earth. The absence of the moon echoes even in our ambitions to leave Earth, altering the trajectory of our species' relationship with the broader cosmos in ways both practical and profound. Whether it slips away quietly or vanishes in a moment, the result is still profound. The consequences of the moon's disappearance would differ dramatically depending on whether it vanished instantaneously or gradually drifted away over millions of years. These two scenarios represent fundamentally different physical processes with vastly different implications for Earth and its inhabitants. Let us explore both possibilities, beginning with the more catastrophic and instantaneous disappearance. If the moon were to somehow vanish in an instant, the immediate effects would be both dramatic and devastating. The most immediate impact would be gravitational. The Moon and Earth exist in a state of mutual gravitational attraction, with each body pulling on the other. This balanced gravitational relationship suddenly broken, Earth would experience what physicists might call gravitational recoil. The ocean tides, which form as bulges of water on opposite sides of the planet due to the Moon's gravitational pull, would suddenly lose their primary driving force. These enormous volumes of water, no longer held in place by lunar gravity, would be set in motion, creating massive tsunami-like waves radiating across the world's oceans. Coastal regions worldwide would face catastrophic flooding as these waters sought a new equilibrium. Unlike normal tsunamis, which arise from localized disturbances like earthquakes or landslides, these waves would affect all of Earth's oceans simultaneously. There would be nowhere on the planet's coastlines entirely safe from their impact. Low-lying coastal cities and communities would face inundation within hours of the Moon's disappearance, with little time for evacuation or preparation. The solid Earth itself would also respond to this sudden gravitational change. Our planet is not completely rigid, but has a certain elasticity, particularly in its crust and mantle. Under the Moon's gravitational influence, the solid Earth actually deforms slightly, creating what scientists call Earth tides that can shift the ground beneath our feet by several centimeters between high and low tide. With the Moon's disappearance, this constant flexing would suddenly cease. The abrupt cessation of these Earth tides would trigger seismic activity worldwide. Fault lines already under stress might suddenly slip, generating earthquakes in regions prone to seismic activity. The magnitude and distribution of these quakes would depend on existing geological stresses, but few continental regions would be entirely spared from at least minor tremors. Coming simultaneously with coastal flooding from oceanic disruption, these seismic events would compound the immediate crisis facing human civilization. Earth's rotation would also be immediately affected. Currently, the Moon's gravitational pull acts as a brake on Earth's rotation, gradually slowing it down over geological time. If this braking force suddenly vanished, Earth's rotation would not immediately speed up, but it would stop slowing down. More significantly, the distribution of Earth's angular momentum would change, potentially causing small but measurable shifts in the planet's rotational behavior that could affect day length and axial orientation. In orbit around Earth, satellites would experience sudden changes in their trajectories. While Earth's gravity is the primary force determining satellite orbits, the Moon's gravitational pull does influence these paths, particularly for satellites in higher orbits. The sudden absence of lunar gravity would cause perturbations in satellite orbits, potentially leading to failures in telecommunications, navigation, weather forecasting, and other satellite-dependent systems. The psychological impact of the Moon's sudden disappearance would be profound. Unlike gradually unfolding climate changes or slowly shifting tides, an instantaneous vanishing would be immediately apparent to everyone on the night side of Earth at the time. The sudden absence of this celestial constant would trigger widespread fear, religious interpretation, and potentially social unrest. Even those with scientific understanding of the situation would find the event deeply unsettling, as it would defy known physics and suggest either previously unknown natural forces, or, more disturbingly, intervention by some incredibly powerful entity or technology. Financial markets would likely crash in the aftermath as the world grappled with coastal disasters and the existential implications of such an inexplicable cosmic event. Insurance systems would be overwhelmed by simultaneous claims from flooding and seismic damage across multiple continents. International aid resources would be stretched beyond capacity as coastal regions worldwide required emergency assistance simultaneously. The scientific community would be thrown into both crisis response and intense investigation. While working to predict and mitigate the physical consequences, researchers would also face the overwhelming question of how such an event could possibly occur, as it contradicts our understanding of physics. The Moon simply cannot disappear under any known natural process. Its instantaneous vanishing would force a fundamental reconsideration of physical law, and potentially open new areas of scientific inquiry, even while dealing with its catastrophic consequences. Now let us consider the alternative scenario: a gradual drift of the Moon away from Earth over millions of years. This scenario actually has a basis in ongoing natural processes, as the Moon is already moving away from Earth at a rate of approximately 3.8 centimeters per year due to tidal interactions. In our hypothetical scenario, we might imagine this process greatly accelerated, but still unfolding over geological rather than human timescales. In this gradual scenario, the immediate catastrophic effects would be avoided. There would be no sudden tsunamis, no worldwide seismic events, no disruption of satellite networks or space missions. Instead, changes would unfold slowly enough for both natural systems and human civilization to adapt progressively rather than facing sudden disaster. Ocean tides would gradually diminish as the Moon moved farther away, growing weaker with each passing millennium. Coastal ecosystems would have time to adapt to the changing tidal patterns, with species gradually shifting their behaviors and distributions in response to the altered environment. Some specialized intertidal species might eventually disappear, but the transition would allow for evolutionary adaptation rather than mass extinction. Earth's rotation would continue to slow, but at a decreasing rate as the Moon's gravitational influence waned. Eventually, as the Moon moved beyond a certain distance, this slowing effect would become negligible. Over millions of years, day length might increase by a small amount before stabilizing, a change slow enough that life would easily adapt to the altered diurnal cycle. The most significant long-term effect would be on Earth's axial stability. As the Moon receded, its stabilizing influence on Earth's tilt would progressively diminish. Over thousands to millions of years, the planet's axis would begin to wobble more dramatically, potentially varying between 0 and 85 degrees over cycles lasting tens of thousands of years. This would cause extreme climate shifts, with some periods seeing no seasons at all and others experiencing hyper-seasonal conditions with extreme temperature variations between summer and winter. These climatic shifts would drive major changes in Earth's ecosystems, forcing species to either adapt, migrate, or face extinction. Given the geological timescale of these changes, evolution would play a significant role in biological responses. New species would emerge, adapted to the more variable climate conditions, while many existing species unable to adjust would disappear. The overall trend would likely be towards more generalist species, with broader environmental tolerances and away from specialists adapted to particular climate niches. Human civilization, assuming it persisted throughout this period, would face enormous challenges adapting to the increasingly unpredictable climate. Agricultural systems would need frequent adjustment as growing conditions shifted. Coastal cities would need to be redesigned as tidal patterns changed. Energy systems dependent on particular climate conditions, from hydropower to solar, would require ongoing modification. The very geography of human settlement might need to shift repeatedly as formerly habitable regions became unviable and new opportunities emerged elsewhere. Yet the gradual nature of these changes would allow for technological and social adaptation that would be impossible in the sudden disappearance scenario. Each human generation would experience conditions only slightly different from their predecessors, allowing for incremental adjustment rather than catastrophic disruption. Knowledge could be accumulated and passed down about how to thrive in the changing conditions, and technologies could be developed specifically to address the emerging challenges. One interesting aspect of the gradual scenario is that humans would observe the Moon's recession and could potentially take scientific or engineering action in response. While currently beyond our capabilities, future civilizations might develop technologies to counteract the Moon's drift, perhaps using gravitational tractors or other advanced physics applications to maintain the Earth-Moon distance at a life-friendly range. The gradual time frame would allow for the development and deployment of such interventions before the most severe consequences manifested. Let us explore the middle timescales between these extremes. What if the Moon disappeared over a period of years or decades? rather than instantly or over geological time. If the moon were to vanish over a period of several years, many of the catastrophic effects of an instantaneous disappearance would be moderated but not eliminated. Ocean tides would gradually diminish, giving coastal communities some time to adapt infrastructure and evacuation plans. But the changes would still outpace natural ecological adaptation. Earth's crust would adjust more gradually to the changing gravitational stresses, potentially leading to increased but not catastrophic seismic activity concentrated along existing fault lines. Climate effects would begin to manifest within decades as the axial stabilization diminished, but would not reach the extreme variations of the geological timescale scenario within a human lifetime. Weather patterns would become increasingly unpredictable, with more extreme events and shifting seasonal boundaries, challenging agricultural systems and natural ecosystems, but not immediately rendering large regions uninhabitable. Human societies would experience significant disruption, but not civilization-threatening collapse. Economic systems would need to adjust to changing coastal infrastructure requirements, agricultural shifts, and increased natural disasters. Some regions would face greater challenges than others, potentially leading to migration pressures and regional conflicts over newly advantageous territories. Yet the gradual enough nature of the changes would allow for international cooperation, technological innovation, and social adaptation that might mitigate the worst potential outcomes. Regardless of the timeframe, any scenario involving the moon's disappearance raises profound questions about Earth's internal dynamics. The moon's gravitational influence affects not just surface phenomena like tides, but may influence processes deep within our planet. Some scientific theories suggest that lunar tidal forces may play a role in maintaining Earth's magnetic field by contributing to movements in the liquid outer core. The disappearance of the moon might therefore have implications for the long-term stability of our magnetic shield, which protects the atmosphere and surface life from harmful solar radiation. The moon also influences Earth's moment of inertia, essentially how its mass is distributed around its axis of rotation. Changes to this distribution can affect the transfer of angular momentum between the solid Earth and its atmosphere and oceans, potentially influencing global circulation patterns beyond the direct effects of axial tilt variations. These complex interactions between planetary rotation, atmospheric dynamics, and oceanic circulation represent feedback systems that might respond in surprising ways to the loss of lunar influence. The differences between sudden and gradual scenarios extend to biological impacts as well. In a sudden disappearance, species that depend on lunar cues for reproduction would immediately face reproductive failure. Corals that spawn synchronously based on lunar phases would release gametes at random times, drastically reducing fertilization success. Sea turtles that nest according to lunar tides might come ashore at inappropriate times or locations, leading to nest failure. These immediate disruptions could drive vulnerable species toward extinction before they could adapt. In a gradual scenario, these same species would experience progressive shifts in their reproductive cues. While still challenging, this would create selection pressure favoring individuals less dependent on precise lunar timing, potentially allowing for evolutionary adaptation over many generations. Some species would likely still decline or disappear, but others might successfully transition to alternative environmental cues for timing their life cycles. When considering solar versus lunar tides, we should note that even after the moon's disappearance, Earth would still experience tides created by the sun's gravitational pull. These solar tides generate about 30 to 40% of our current total tidal force. Coastal regions would still experience high and low tides, but with significantly reduced range and shifted timing, instead of the current semi-diurnal pattern in most locations. With 2 high and 2 low tides daily, many areas would shift to a purely diurnal pattern, with 1 high and 1 low tide per day. This reduced tidal range would still support some intertidal ecosystems, albeit with compressed zonation and reduced biodiversity. For human society, different disappearance timelines would create vastly different adaptation challenges. An instantaneous vanishing would represent an unprecedented crisis demanding immediate emergency response, from coastal evacuations to infrastructure repairs to managing public fear and potential panic. The scientific community would be simultaneously trying to understand an impossible event while helping predict and mitigate its consequences, creating unprecedented tensions between theoretical and applied science. A gradual recession would present more manageable adaptation challenges, but would require long-term planning beyond the timeframes that human institutions typically manage successfully. Political systems operating on election cycles of a few years would need to implement policies addressing changes unfolding over decades or centuries. Economic systems focused on quarterly profits would need to account for environmental transformations affecting fundamental resource availability. This mismatch between human decision-making timeframes and gradual cosmic changes would present significant governance challenges. What becomes clear in examining these differing timelines is that while the physical end state might be similar, a moonless Earth with altered climate patterns and simplified ecosystems, the journey to that state and the capacity for adaptation along the way differ enormously depending on how quickly the change occurs. Whether it slips away quietly over eons or vanishes in a catastrophic moment, the result is still profound. But the story of how Earth and its inhabitants respond would follow dramatically different paths. Could humanity recreate what the universe once gifted us freely? If the moon were to disappear, could we replace it? This question bridges science fiction and theoretical engineering, challenging us to consider whether human ingenuity could substitute for a natural satellite that has influenced Earth for billions of years. While currently far beyond our technological capabilities, exploring this question allows us to appreciate both the moon's complexity and the potential boundaries of future human achievement. The moon is massive, with a weight of approximately 73 sextillion kilograms, about 1/81st of Earth's mass. Its diameter spans 3,474 kilometers. These dimensions alone present an extraordinary challenge. No human construction has ever approached even a tiny fraction of this scale. The largest structures humans have built, like the Great Wall of China or the Three Gorges Dam, are infinitesimal compared to the moon. Even if we could somehow construct an object of lunar size, the energy requirements to place it in orbit would exceed our current global energy production by many orders of magnitude. Given these physical constraints, a direct replacement, a new moon identical to our current one, lies firmly in the realm of impossibility for the foreseeable future of human civilization. However, we might consider more modest approaches that could replicate specific lunar functions rather than the moon itself. Let us explore some theoretical possibilities, beginning with the moon's most noticeable feature, its light. Could we create artificial moonlight? This might be the most achievable aspect of lunar replacement. Large orbital mirrors could potentially reflect sunlight down to Earth during night hours, creating zones of illumination similar to moonlight. Such concepts have already been proposed for other purposes, such as extending daylight hours in northern cities or providing light for nighttime disaster response. Solar reflectors in orbit could be designed to provide illumination similar in intensity to the full moon, though they would likely cover only specific regions rather than the entire night side of Earth. The engineering challenges would be substantial but not insurmountable. Such reflectors would need to be enormous, with surface areas measured in square kilometers, and would require precise station keeping to maintain proper orientation. The materials would need to withstand the harsh environment of space while maintaining reflectivity over long periods. Launch costs would be considerable, though significantly less than any attempt to create a moon-sized object. With sufficient motivation and resources, future civilizations might construct networks of such reflectors to provide artificial moonlight to selected regions. However, visual appearance would be quite different. Rather than a single circular celestial body, these reflectors would appear as bright points or patches of light moving across the night sky. they could not replicate the cultural and psychological aspects of the moon's appearance, its familiar face that has inspired human art and mythology for millennia. The aesthetic and emotional loss would remain, even if functional illumination were restored. What about the moon's gravitational influence? This presents a far greater challenge. The moon's mass creates tidal forces that shape our oceans, stabilize Earth's axial tilt, and influence Earth's rotation. Replicating these effects would require creating gravitational forces of similar magnitude, which fundamentally requires mass. There is simply no way to generate significant gravitational influence without an object of substantial mass. One theoretical approach might involve positioning several large asteroids in Earth orbit. The largest known asteroids, like Ceres, Vesta, and Pallas, have masses measured in the quintillions of kilograms, still far smaller than the Moon, but potentially large enough to exert measurable gravitational effects. Moving such objects from their current orbits in the asteroid belt to Earth orbit would require technologies far beyond our current capabilities, including propulsion systems that could operate continuously for decades and energy sources of unprecedented power. Even if such a project were technically feasible in the distant future, the risks would be enormous. Miscalculations in orbital mechanics could send these massive objects crashing into Earth, causing extinction-level events. The gravitational perturbations during their approach could disrupt Earth's existing orbit or affect other planets in unpredictable ways. The cure might well prove more dangerous than the disease of lunar absence. A more modest approach might involve creating a network of smaller artificial satellites specifically designed to mimic some of the Moon's stabilizing effects on Earth's axis. While they could not generate significant tidal forces, they might be positioned in such a way as to exert small but precisely calculated gravitational tugs that cumulatively help maintain Earth's axial orientation. Such a system would require exquisite precision in orbital calculations and continuous adjustment over centuries or millennia. What about the ecological functions of lunar tides? Here, human engineering might offer some interesting possibilities. Coastal ecosystems that depend on the rhythm of tides might be partially supported by engineered tidal systems. Massive pumping stations could potentially move seawater in and out of selected coastal areas on a schedule mimicking natural tides. While enormously energy-intensive and limited to specific protected regions, such systems might preserve some of the unique intertidal habitats that would otherwise be lost. Similarly, artificial light cycles might help preserve some of the biological rhythms that depend on lunar illumination. Coordinated lighting systems in marine reserves could potentially maintain the spawning cues that corals and other organisms rely on. While impossible to implement on a global scale, targeted interventions might preserve pockets of lunar-dependent biodiversity that would otherwise disappear. For human cultural and spiritual needs, virtual reality and advanced projection technologies might create compelling simulations of the Moon for aesthetic and psychological purposes. Imagine vast domed ceilings in cities displaying a perfect simulation of the night sky, complete with lunar phases, or personal devices that overlay the image of the Moon on one's actual view of the night sky. While not replacing the real thing, such technologies might help maintain cultural connections to lunar imagery and preserve artistic and spiritual traditions that reference the Moon. From a scientific perspective, the loss of the Moon as a natural laboratory and exploration destination might be partially offset by constructing large space stations or habitats at the former Earth-Moon Lagrange points. These facilities could serve some of the research functions previously conducted on the lunar surface, particularly in areas of astronomy, solar observation, and Earth systems monitoring. While not replicating the geological value of the Moon, they might preserve some of its scientific utility. One more speculative possibility involves planetary engineering to compensate for the Moon's absence. If Earth's rotation began to accelerate without lunar braking, future civilizations might develop technologies to artificially slow it, perhaps by constructing massive tidal power systems that extract rotational energy. Similarly, if axial wobble began to destabilize climate patterns, massive flywheel systems incorporated into Earth's crust might theoretically provide some stabilizing influence. Such concepts remain deeply speculative and would require engineering on scales far beyond current capabilities, but they represent theoretical approaches to addressing specific consequences of lunar absence. Perhaps the most ambitious theoretical replacement would involve creating a completely new sister planet for Earth. Though currently in the realm of science fiction, future civilizations with sufficient mastery of physics and planetary engineering might attempt to aggregate matter from the asteroid belt or outer solar system to construct a new planetary body. This would be a multi-century or even multi-millennium project, gradually building a substantial mass in an orbit designed to replicate the Moon's stabilizing effects. While far beyond foreseeable technology, it represents the logical endpoint of replacement strategies based on mimicking the Moon's mass and gravitational influence. All of these approaches highlight a fundamental limitation. Any artificial replacement would likely require continuous maintenance and adjustment, whereas the Moon has provided its services autonomously for billions of years. Natural systems possess a self-regulating stability that engineered solutions struggle to match. The Moon maintains its orbit through the natural balance of gravitational forces. Any artificial replacement would likely require constant monitoring and correction to prevent degradation or failure. There's also the question of energy requirements. The Moon performs its functions without consuming energy beyond the gravitational potential established during its formation. Any artificial replacements would require ongoing energy inputs, likely at scales that would strain even highly advanced civilizations. The efficiency of natural systems often far exceeds what engineering can achieve, particularly for processes operating at planetary scales over geological time periods. When considering these challenges, we confront the profound improbability of fully replacing the Moon through technology alone. Perhaps the more valuable insight is recognizing the extraordinary good fortune represented by the Moon's presence in the first place. The specific size, mass, distance, and orbital characteristics of our Moon create a set of influences remarkably beneficial for Earth's stability and the evolution of complex life. This appears to be relatively uncommon in planetary systems based on current exoplanet observations. Rather than focusing on replacement, a more practical approach for any future human civilization facing lunar disappearance might be selective adaptation and mitigation. This could involve preserving particularly valuable lunar-influenced ecosystems through localized engineering, developing social and agricultural systems adapted to more variable seasonal patterns, and creating cultural and aesthetic substitutes for the Moon's presence in human experience. There's a philosophical dimension to this question as well. The impulse to replace the Moon technologically reflects a particular relationship with nature based on control and engineering. An alternative approach might involve adapting human systems to the changed circumstances, developing new cultural and biological relationships with a moonless Earth, rather than attempting to force the old patterns to continue artificially. This perspective would view the Moon's absence as an opportunity for new, evolutionary and cultural pathways, rather than simply a loss to be remediated. The question of whether we could artificially replace the Moon ultimately reveals more about human ambition and the limits of technology than it provides practical solutions. Our current engineering capabilities fall orders of magnitude short of what would be required for meaningful lunar replacement. Even the most advanced civilizations imaginable might find it more practical to adapt to lunar absence than to recreate what the Moon once provided. Yet the question itself has value, inviting us to appreciate the extraordinary complexity of Earth's relationship with its satellite. By contemplating what it would take to replace the Moon, we gain a deeper understanding of the natural systems we often take for granted. Could humanity recreate what the universe once gifted us freely? Perhaps not. But in asking the question, we develop greater appreciation for the remarkable cosmic partnership that has shaped our world for billions of years. With our protector gone, Earth stands bare under the fire of the cosmos. Among the Moon's many influences on Earth, One of the least appreciated, yet potentially most significant, is its role as a protective shield. Our lunar companion has been absorbing cosmic impacts for billions of years, its cratered face bearing silent testimony to collisions that might otherwise have struck our planet. If the moon were to disappear, Earth would lose this celestial bodyguard, potentially facing an increased bombardment from space. To understand the moon's protective function, we must first consider the environment of our solar system. While appearing serene from our perspective on Earth, the space around us is anything but empty. It contains countless objects, from dust-sized particles to massive asteroids, moving at tremendous velocities. These objects range from the relatively predictable, like comets with well-calculated orbits, to the unexpected, like interstellar visitors similar to Oumuamua that pass through our solar system from beyond. Throughout its history, Earth has experienced numerous impact events, from relatively small meteorites that reach the surface to civilization-threatening collisions like the Chicxulub impact 66 million years ago that contributed to the extinction of non-avian dinosaurs. These impacts have shaped Earth's evolutionary history, creating extinction events that open opportunities for new species while closing the chapter on others. The Moon, lacking atmosphere, flowing water, or active plate tectonics, preserves its impact history much more visibly. Its surface has accumulated approximately 300,000 craters larger than 1 kilometer in diameter, with countless smaller impact sites. Each of these represents a collision with a cosmic object, from micrometeorites to substantial asteroids. The largest impact basins, like South Pole, Aitken, with a diameter of approximately 2,500 kilometers, testify to truly catastrophic events early in our solar system's history. But how exactly does the Moon protect Earth? There are several mechanisms at work, some direct and others more subtle. The most straightforward protective function is as an impact absorber. The Moon presents a substantial target in Earth's vicinity, its gravitational field capturing or deflecting objects that might otherwise continue toward Earth. While much smaller than our planet, with a surface area approximately 1/4 that of Earth, the Moon still intercepts a significant number of potential impactors. Over the billions of years of Earth's history, the Moon has likely absorbed thousands of impacts that might otherwise have struck our planet. This shielding function was particularly important during the period known as the Late Heavy Bombardment, approximately 4 billion years ago. During this chaotic epoch, the inner solar system experienced an intensified barrage of impacts as gravitational interactions with the giant planets scattered numerous objects into Earth-crossing orbits. The Moon, already in place following its formation about 4.5 billion years ago, absorbed many of these impacts, potentially sparing Earth from even more catastrophic bombardment during this critical early period when life may have been first emerging. Beyond simply absorbing impacts that might have hit Earth directly, the Moon also affects the orbital dynamics of near-Earth objects. Its substantial mass, about 1/81st of Earth's, creates a gravitational influence that extends throughout cislunar space, the region between Earth and the Moon. This influence can alter the trajectories of passing objects, sometimes deflecting potential Earth impactors, and other times potentially directing objects toward Earth that might otherwise have missed. The net effect of these gravitational influences is complex and depends on the specific objects and their approach vectors. Computational models suggest that while the Moon occasionally diverts objects toward Earth, it more frequently acts as a protective influence, particularly for certain approach angles. Over billions of years, this gravitational shepherding likely prevented numerous potential impacts. If the Moon were to disappear, these protective functions would cease. Earth would face the solar system's bombardment alone, without its celestial shield. While difficult to quantify precisely, astronomical models suggest that the impact rate on Earth might increase by approximately 10 to 20% without the Moon's presence. This may not sound dramatic, but over geological timescales, it represents a substantial increase in potentially catastrophic events. Beyond the direct impacts, the Moon also shields Earth from less obvious cosmic threats. Dust and smaller particles from comets and asteroids create meteor showers when Earth passes through their debris streams. The Moon absorbs some of this material that would otherwise enter Earth's atmosphere. The Moon also occasionally shields Earth from the effects of solar storms when properly aligned between Earth and the Sun. Perhaps most significantly, from a human perspective, the Moon has helped us develop awareness of cosmic impact threats. By presenting its heavily cratered face to our telescopes, and eventually our visiting astronauts, the Moon provided undeniable evidence that large-scale impacts are not merely theoretical, but have occurred repeatedly throughout our solar system's history. This visible record helps scientists recognize impact craters on Earth and develop understanding of cosmic collisions as an ongoing process, rather than just an ancient phenomenon. This awareness has spurred the development of programs to detect and track near-Earth objects that might pose impact threats. Organizations like NASA's Planetary Defense Coordination Office now monitor thousands of asteroids and comets, calculating their orbits to identify potential future collisions with Earth. This detection work, inspired partly by studying the Moon's impact history, represents humanity's first steps toward developing an active planetary defense capability. In a world without the Moon, the slightly increased impact threat would unfold over geological timescales rather than human ones. The difference would be statistically significant over millions of years, but might not result in any noticeable increase in impacts within a human lifetime, or even over several generations. However, over deeper time, the compounding of this increased risk would potentially influence Earth's biological evolution and geographical features. For life on Earth, cosmic impacts represent both threat and opportunity. Major impacts create extinction events that eliminate certain species while opening ecological niches for others. The dinosaur-killing Chicxulub impact, for instance, helped create conditions that eventually allowed mammals to diversify and dominate, ultimately leading to human evolution. In a moonless Earth with a modestly increased impact rate, such evolutionary turning points might occur somewhat more frequently, potentially accelerating the pace of evolutionary change while also increasing extinction rates. Interestingly, the Moon has also contributed to Earth's capacity to recover from major impacts. By stabilizing our planet's axial tilt, the Moon helps maintain relatively predictable climate zones that can serve as refugia for species during global catastrophes. Without the Moon, Earth's more chaotic axial wobble might create additional challenges for species trying to survive in the aftermath of a major impact when ecosystems are already under extreme stress. Modern civilization, with its interconnected systems and concentrated population centers, may be particularly vulnerable to impact effects. Beyond the direct destruction at an impact site, secondary effects like atmospheric dust causing global cooling, tsunamis from ocean impacts, or electromagnetic pulse effects from atmospheric explosions could disrupt global systems. The Moon's modest shielding function thus takes on additional significance for a technologically dependent civilization. Humanity's growing awareness of impact threats has led to consideration of active planetary defense strategies. Concepts include systems to detect potentially hazardous objects years in advance, then deflect them using technologies ranging from gravity tractors that subtly alter an asteroid's orbit through gravitational attraction to kinetic impactors that would physically knock an object onto a safer trajectory. In considering the Moon's protective role, we should note that not all cosmic objects approach from directions where the Moon might intercept them. The Moon orbits in a fairly narrow band around Earth's equator, meaning objects approaching from high inclinations toward Earth's poles would never encounter the lunar shield. The Moon's protection has always been partial rather than complete, a reduction of risk rather than its elimination. The psychological dimension of losing this protection deserves consideration as well. Though most humans don't consciously consider the Moon as a shield, there's something reassuring about having another substantial world sharing our cosmic neighborhood. If the Moon were to disappear, our planet might feel more isolated and vulnerable in the vastness of space. With our protector gone, Earth would stand more exposed to the fire of the cosmos. The physical shield of the moon's mass and the gravitational influence of its presence would no longer divert the small fraction of cosmic objects that might otherwise strike our world. And in losing this protection, we would lose something more, a visible reminder of both cosmic violence and the profound good fortune that has allowed complex life to flourish on our world for hundreds of millions of years. The moon is not just out there, it's within us. The disappearance of the moon would trigger not only physical and biological changes to our planet, but profound psychological effects as well. The moon has been a constant companion throughout human evolution and cultural development. Its presence has shaped our minds, our emotions, our sense of time and place, in ways both obvious and subtle. If it were to vanish, the impact on human psychology might be as significant as any of the physical consequences we've explored. To understand these psychological effects, we must first consider the moon's role in human consciousness. Unlike distant stars or even other planets, the moon appears as a distinct world in our sky, large enough to show visible features to the naked eye. It changes in a predictable yet visually dramatic cycle, waxing and waning through its phases. It illuminates the night, turning darkness into a different kind of experience than complete blackness. These qualities have made the moon a central object in human awareness since our earliest days as a species. The most immediate psychological impact of the moon's disappearance would be a sense of profound loss and disorientation. For people alive at the time of its vanishing, the moon represents a foundational element of reality, something so constant that its absence would create cognitive dissonance. This wouldn't be like the disappearance of a star or even a mountain, but the removal of a cosmic presence that has framed human experience for countless generations. The night sky would suddenly feel emptier, darker, and perhaps more threatening. The moon provides not just physical illumination, but psychological comfort, a familiar presence that has watched over humanity throughout our existence. Without it, the night might become a more alienating experience, particularly for those who live in areas without significant artificial lighting. The primordial human fear of darkness might reassert itself more strongly without the moon's gentle glacial glow occasionally brightening our nights. Temporal disorientation would likely follow as well. The lunar cycle has provided humans with a natural time marker midway between the day and the year, helping to organize our sense of time's passage. Many people, even in modern society, maintain awareness of the lunar phase, sometimes unconsciously. Without this cosmic clock, our psychological experience of time might become more binary, divided simply between day and year without the intermediate lunar rhythm that has always existed in human experience. The moon has also played a crucial role in human navigational psychology. Before modern instrumentation, the moon served as both illumination for nighttime travel and a directional reference point. Many traditional wayfinding systems, particularly those developed by seafaring cultures, incorporate careful observation of the moon's position and phase. Without the moon, these navigational frameworks would lose an essential component, potentially creating a deeper sense of lostness or disconnection from traditional knowledge. Sleep patterns, too, would likely be affected by a moonless sky. Research suggests that human sleep can be influenced by lunar phases, with some studies indicating that sleep duration and quality vary slightly throughout the lunar cycle. While artificial lighting has diminished these effects in modern life, the complete absence of the moon might still affect our circadian biology in subtle ways. More significantly, people who live in areas with limited artificial lighting would lose an important natural light source that has influenced human sleep-wake cycles for millennia. For many individuals, the moon holds significant emotional and spiritual meaning. It serves as an object of wonder, contemplation, and even worship across diverse cultures. The sense of connection to something larger than oneself, something cosmic yet intimately familiar, that the moon provides would be irretrievably lost. This cosmic loneliness might be particularly acute for those who have found personal meaning in the moon's presence, whether through spiritual practice, astronomical interest, or simply aesthetic appreciation. Children born after the moon's disappearance would develop in a fundamentally different psychological environment than all previous human generations. They would learn about the moon only through images and descriptions, never experiencing the visceral impact of watching a full moon rise, observing its features through a small telescope, or seeing it illuminate a landscape. Their conception of the cosmos would be formed without one of the most immediate and dramatic examples of worlds beyond Earth visible to the naked eye. Would these moonless generations have a different relationship with the night, with time, with the cosmos itself? Would their dreams and imagination develop along different paths without the moon as a universal reference point and symbol? These questions touch on deep aspects of human psychological development that we can only speculate about, yet they suggest how profoundly the moon has shaped human consciousness throughout our species' existence. The moon has served as a powerful symbol in the human unconscious, appearing in dreams, mythology, and creative expression across all cultures and eras. Its associations with femininity, cyclical change, illumination in darkness, and otherworldly mystery have created a rich symbolic vocabulary that informs human psychology at levels deeper than conscious awareness. The loss of this primary symbol might create a void in the collective unconscious, a missing archetype that has helped humans organize and express certain categories of experience. Consider how the moon has functioned in psychological development across cultures. Children typically recognize the moon as one of their first celestial objects, often forming emotional attachments to it as a friendly presence in the night sky. Many parents and children share moon watching as a bonding experience, creating psychological associations between the moon and feelings of security, wonder, and connection. Without the moon, these developmental experiences would be lost, replaced perhaps by different celestial observations, but lacking the specific qualities that lunar observation provides. The moon's phases have also served as a natural introduction to the concept of change within constancy, a fundamental psychological pattern that helps humans understand transformation. The moon changes its appearance dramatically, yet predictably, remaining fundamentally the same object, while visually transforming through its cycle. This accessible cosmic example of permanent impermanence has helped countless generations grasp similar patterns in their own lives and environments. Future generations would need to find different natural models for this important concept. For those who study or practice astrology, the moon's disappearance would represent a catastrophic disruption to a symbolic system that has influenced human psychological interpretation for millennia. While scientific evidence doesn't support astrological claims, the moon's central role in astrological systems has nonetheless shaped how many people throughout history have understood themselves and others. This interpretive framework would require fundamental revision, creating psychological disruption for those who use it to organize their understanding of human personality and behavior. Artists, writers, musicians, and other creative individuals would lose a primary source of inspiration and symbolism. The moon has featured prominently in human creative expression since our earliest artistic efforts, providing rich metaphorical material and visual inspiration. From poetry comparing lovers to the moon, to visual art capturing its light on landscapes, to music evoking its mysterious presence, lunar imagery permeates human creativity. Without the moon as a reference point, creative expression would need to find alternative cosmic symbols, potentially developing new metaphorical languages over time. The psychological impact would vary significantly depending on cultural context. Cultures with strong lunar connections in their traditional practices, mythologies, and calendars would experience a deeper sense of disruption and loss. Communities that organize important festivals and observances according to lunar cycles would need to develop alternative timing systems, potentially weakening connections to cultural heritage. The psychological effects of losing these cultural reference points might include increased feelings of disconnection from ancestral traditions and collective identity. For modern urban dwellers already disconnected from the night sky by light pollution, the psychological impact might initially seem less severe. Yet even in brightly lit cities, the full moon remains visible, providing one of the few remaining direct connections to cosmic cycles. Without this connection, urban psychological experience might become even more detached from natural rhythms, potentially deepening the sense of separation from the natural world that many already experience in highly developed environments. Interestingly, the moon's absence might eventually intensify interest in and awareness of other celestial objects. Without lunar light washing out fainter stars, the night sky would appear more densely populated with stars. Perhaps the visible planets would take on greater psychological significance, or star patterns would become more central to human orientation and storytelling. Human psychology tends to seek replacement symbols when important ones are lost, suggesting that over generations, other cosmic features might partially fill the void left by the moon. The experience of darkness itself would be transformed in a moonless world. Currently, human experience of night includes a range of illumination levels, from the relative brightness of a full moon night to the profound darkness of a new moon. Without the moon, nights would become more consistently dark, interrupted only by starlight and artificial lighting. This more binary experience of light and darkness might subtly influence human psychology, perhaps strengthening the metaphorical association between darkness and the unknown, or threatening while reducing the experience of illumination as something that exists in degrees rather than absolutes. For scientific understanding and education, the moon's absence would remove a powerful tool for inspiring cosmic awareness. The moon has served as an entry point for countless individuals into astronomy and broader scientific interest. Its accessibility to direct observation, the drama of its phases, and its visual detail when viewed through even simple telescopes have made it an ideal first object for developing observation skills and cosmic curiosity. Educational approaches would need to find alternative celestial objects to serve this introductory function, likely with less immediate psychological impact than the conspicuous and changing moon. Some psychological effects might manifest in dreams and the unconscious mind. The moon has been a frequent element in human dreams across cultures and eras, its appearance in dreamscapes carrying various symbolic meanings. Dream researchers have noted that celestial objects in dreams often connect to transcendent themes and expanded awareness. Without the moon, as both a real presence in waking life and a dream symbol, the architecture of human dreaming might subtly shift, perhaps finding new symbols to express similar psychological content, or perhaps losing certain categories of dream experience altogether. A particularly interesting question concerns whether humans would invent substitutes for the missing moon. Might we create art, rituals, or even technologies that attempt to recreate certain psychological functions the moon once served? Historical examples suggest this possibility, as humans have often created symbolic substitutes for lost natural phenomena. Perhaps annual commemorations would mark the moon's former phases, or artistic installations might project lunar-like illumination during certain times. These substitutions would acknowledge the psychological need the moon once fulfilled, while adapting to its absence. For people with certain psychological conditions, the moon's disappearance might have specific effects. Those experiencing conditions involving heightened sensitivity to environmental changes, such as certain forms of anxiety or sensory processing differences, might find the altered night environment particularly disorienting. Conversely, conditions sometimes anecdotally linked to lunar phases, like increased emergency room visits or psychiatric admissions during full moons, might show altered patterns, though scientific evidence for such lunar effects remains limited and contested. Over generations, the psychological impact would transform from active loss to historical curiosity. Children born to a moonless Earth would never experience the direct sense of absence felt by those who had known the moon. Instead, they would learn about the moon as a historical fact, something that once existed but no longer does, like extinct animals or vanished civilizations. Their psychological relationship to the concept of the moon would be fundamentally different, intellectual rather than experiential, shaped by images and descriptions rather than direct perception. This generational difference might create a fascinating divide in human experience. Those who remembered the moon might speak of it with a nostalgia and emotional connection that younger generations would find difficult to fully comprehend. Stories about walking under moonlight or watching lunar eclipses would take on an almost mythical quality for those who had never experienced these phenomena. The moon might gradually transition from lived experience to cultural memory, its psychological impact preserved in art and literature, but no longer directly accessible. What emerges from this exploration of psychological effects is a picture of how deeply the moon has shaped human consciousness, and how profoundly its absence would affect our species' mental and emotional experience. The moon is not merely an external object we observe, but has become integrated into human psychology in ways both obvious and subtle. Its disappearance would create not just a gap in the night sky, but a void in human psychological experience that would transform our relationship with night, time, and the cosmos itself. The moon is not just out there, it's within us. Its rhythms have become our rhythms. Its light has illuminated not just our nights, but our understanding of ourselves as beings connected to cosmic cycles and worlds beyond our own. In losing the moon, we would lose not just a celestial body, but a piece of our psychological heritage, a constant companion that has helped shape what it means to be human on this particular planet, under this particular sky. Even in the vastness of space, such companions are rare and perhaps irreplaceable. If the moon were to disappear, could Earth naturally acquire another satellite? Might some cosmic process deliver a replacement moon to orbit our planet, restoring some of the functions our current moon provides? This question invites us to explore the mechanics of satellite capture, the likelihood of such an event, and whether any potential replacement could truly fill the role that our moon has played in Earth's story. The formation of Earth's moon was an extraordinary event, the product of a specific and dramatic moment in our planet's early history. According to the prevailing giant impact hypothesis, the moon formed when a Mars-sized object called Theia collided with the proto-Earth approximately 4.5 billion years ago. This collision ejected enormous quantities of material into orbit around Earth, which eventually coalesced to form our lunar companion. This was not a common occurrence, but a relatively rare event in planetary evolution. For Earth to naturally acquire another moon, one of several scenarios would need to unfold. The most plausible would involve the gravitational capture of a passing asteroid or other solar system object. For such a capture to occur, the object would need to pass through a very specific region of space around Earth at just the right velocity. Too fast, and it would simply fly by. Too slow, and it might collide with Earth instead of entering orbit. Additionally, to achieve a stable orbit, the object would typically need to lose energy during this encounter. In the vacuum of space, this generally requires a complex gravitational interaction involving at least 3 bodies, such as Earth, the passing object, and the Sun or perhaps Jupiter. These conditions make natural satellite capture an extremely rare event, especially for a planet like Earth that resides in the inner solar system where object velocities tend to be higher. The likelihood of capturing an object large enough to meaningfully replace the moon is vanishingly small. While Earth might occasionally temporarily capture very small asteroids as mini-moons that orbit for a few months or years before escaping, the capture of anything approaching lunar dimensions would be an extraordinary cosmic coincidence. Most asteroids large enough to serve as meaningful lunar replacements follow stable orbits that are unlikely to bring them into Earth's gravitational sphere of influence in the first place. Even if Earth were to capture another object, its characteristics would almost certainly differ dramatically from our current moon. The composition, density, orbital parameters, and size would likely vary significantly. These differences would determine what lunar functions the new satellite could or couldn't replace. Consider size and mass. Our moon is unusually large relative to its parent planet, with a diameter about 1/4 that of Earth and a mass about 1/81st of Earth's. This substantial size is what enables the moon to exert significant gravitational influence on Earth, creating meaningful tides and helping stabilize our axial tilt. Most asteroids, even the largest ones like Ceres, are much smaller than our Moon. Ceres, the largest object in the asteroid belt, has only about 1% of the Moon's mass, meaning its gravitational effects would be proportionally smaller. The orbit of any captured object would also likely differ from the Moon's nearly circular path around Earth's equator. Captured bodies tend to initially follow more elliptical orbits, often at significant inclinations to the equatorial plane. These orbital characteristics would produce different tidal patterns and would not stabilize Earth's axial tilt in the same way our current Moon does. Over time, tidal interactions might gradually circularize the orbit, but this process would take millions of years or longer. The composition of a captured asteroid would also differ from our Moon. Our lunar companion shares many chemical similarities with Earth's mantle because it formed from material ejected from our planet. This is not true of asteroids, which formed in different regions of the solar system under different conditions. A carbonaceous asteroid would have higher water content than our relatively dry Moon, while a metallic asteroid would have a much higher density. These compositional differences would affect everything from the object's appearance in our sky to its long-term orbital evolution. From a visual perspective, any replacement Moon would present a different face to Earth observers. Our current Moon appears as a distinct disk with clearly visible surface features and a predictable cycle of phases. A smaller captured asteroid might appear as little more than a bright point of light to the naked eye, more like a brilliant star or planet than what we typically think of as the Moon. It would still cycle through phases, but might not provide the significant illumination or distinctive visual presence that has inspired human culture for millennia. The most likely natural scenario would not involve one large replacement Moon, but rather the temporary capture of multiple small asteroids over geological time. Earth might host a series of mini-moons, each perhaps a few hundred meters or a few kilometers in diameter, that would orbit for periods ranging from months to centuries before escaping again into solar orbit. These objects would be scientifically interesting, but would not replicate the Moon's major influences on Earth systems. Looking beyond asteroids, could a more exotic scenario provide Earth with a replacement Moon? Might a passing rogue planet that has been ejected from its original solar system be captured by Earth? While theoretically possible, such an event would be extraordinarily unlikely, especially without catastrophic consequences. The gravitational dynamics involved in capturing such a massive object would likely severely disrupt Earth's orbit around the Sun, potentially rendering our planet uninhabitable in the process. The cure, in this case, would be worse than the disease of moonlessness. Another theoretical source for a replacement Moon might be one of the moons of Jupiter or Saturn that gets gravitationally ejected from its current orbit due to some major disturbance. However, for such a Moon to end up in Earth's vicinity with the precise velocity needed for capture would require an extraordinary sequence of gravitational interactions, making this scenario exceedingly improbable. Additionally, any Moon large enough to meaningfully replace our current satellite would likely be traveling too fast after ejection to be captured by Earth's relatively modest gravitational field. From an astronomical perspective, Earth's possession of such a large Moon is somewhat unusual. While many planets in our solar system have moons, the Earth-Moon system is exceptional in having such a large satellite relative to its parent planet. Mars has 2 tiny moons, likely captured asteroids, that exert minimal influence on the red planet. Jupiter and Saturn host numerous moons, but even their largest satellites represent a much smaller fraction of their parent planet's mass than our Moon does relative to Earth. Venus and Mercury have no moons at all. This exceptionality suggests that the specific conditions that gave Earth such a large, influential Moon might be rare, both in terms of occurrence and timing. The giant impact that formed our Moon happened at a particular moment in the solar system's evolution when such massive collisions were becoming less common but still possible. The window for such events has likely closed in our more mature solar system, where orbital paths have largely stabilized. The rarity of Earth's situation becomes even clearer when we consider that the Moon is gradually retreating from Earth due to tidal interactions. It moves away at approximately 3.8 centimeters per year. This ongoing process means that the current Earth-Moon relationship, which has been so influential for our planet's development, represents a specific chapter in a longer cosmic story. The Moon was once much closer to Earth, creating more extreme tides and effects, and in the distant future, it will be much farther away, exerting less influence. Any replacement Moon would not recreate this particular history or relationship. From a biological perspective, could another Moon adequately replace the ecological and evolutionary functions of our current satellite? Many species have evolved behaviors and life cycles precisely attuned to the specific characteristics of our Moon, including its size, brightness, orbital period, and tidal effects. A different Moon with different properties would create different selective pressures and environmental cues. While life would eventually adapt to these new conditions, the transition would likely involve substantial ecological disruption and potentially the extinction of species most dependent on current lunar conditions. For human cultural and psychological needs, a smaller, less visually prominent replacement Moon would likely fail to fill the role our current Moon has played throughout human history. The Moon's size and brightness in our sky have made it a universal reference point, visible to all humans regardless of location or technological development. A smaller replacement might be tracked by astronomers, but would not serve as the same kind of collective focal point for human experience and meaning-making. Time measurement, which has been fundamentally shaped by lunar cycles across human cultures, would not benefit from the same clear visual cues if Earth captured a smaller asteroid as a mini-moon. The precise 29.5-day cycle of lunar phases has provided a natural calendar unit, the month, that bridges the gap between the day and the year. A smaller replacement Moon with a different orbital period would not offer the same intuitive timekeeper function. There is, perhaps, a philosophical dimension to this question as well. The specific Moon we have has been integral to Earth's developmental story and to humanity's understanding of our place in the cosmos. Its particular characteristics, formed through its specific history, have shaped our world in ways unique to this relationship. In this sense, our Moon might be truly irreplaceable, not just practically, but conceptually. A different lunar companion would create a different Earth and a different human experience, not simply a restoration of what was lost. This irreplaceability extends to the physical effects as well. The precise stabilizing influence our Moon exerts on Earth's axial tilt, for instance, depends on very specific parameters of mass, distance, and orbital characteristics. A different satellite with different properties would create different patterns of stability or instability for our planet's rotation. The Earth-Moon system, as we know it, represents a particular configuration that has proven remarkably hospitable for the development of complex life. Any replacement would create a new and different configuration, not necessarily as conducive to the conditions we associate with Earth. In the vastly improbable event that Earth did naturally capture another large satellite, the transition period would itself be potentially catastrophic. The gravitational interactions between Earth, the existing Moon, and a new massive object entering the picture would create chaotic orbital dynamics. Tidal forces would fluctuate unpredictably. Orbital resonances could develop that might eventually eject one or both moons, or potentially cause one to crash into Earth or the other satellite. The process of establishing a new stable configuration would involve a period of gravitational chaos that would severely impact Earth's systems. What emerges from this exploration is a picture of just how special and unlikely our current Earth-Moon relationship truly is. The specific satellite we have, with its particular size, composition, orbit, and history, represents a cosmic arrangement that would not be easily or exactly replicated by natural processes. While Earth might someday host other satellites, through either natural capture or future human intervention, they would create new relationships rather than restore what was lost. Even in the vastness of space, such companions are rare, and perhaps irreplaceable. Our moon is not simply a generic satellite, but a specific world with a specific shared history with Earth. A partner in a cosmic dance that has shaped our planet's development in ways that no chance replacement could precisely duplicate. If the moon were to disappear, the vacancy left in Earth's sky might occasionally host temporary visitors, but the particular relationship that has helped make our world what it is would be gone forever. There are Earths out there without moons, but none of them are ours. As we contemplate the disappearance of our moon, a fascinating question emerges. What would Earth have been like if it had never had a moon at all? How might our planet have developed differently if the giant impact that created the moon had never occurred? This thought experiment allows us to explore not just the effects of losing the moon now, but the profound ways in which our lunar companion has shaped Earth's entire evolutionary story. The absence of a moon is not unusual in our solar system. Of the 4 rocky inner planets, 2 lack natural satellites. Venus, similar to Earth in size and composition, has no moon. Mercury, the smallest and innermost planet, is also moonless. Beyond our solar system, astronomers speculate that many rocky planets throughout the galaxy likely formed without large moons like ours. A moonless Earth would have been cosmologically unremarkable, yet profoundly different from the world we know. Let us begin at the beginning, with the formation of the Earth itself. Current scientific understanding suggests that the impact event that created the moon approximately 4.5 billion years ago dramatically altered Earth's development. This massive collision with the Mars-sized object called Theia not only created our satellite, but likely affected Earth's mass, composition, rotation, and even the length of its day. Without this impact, Earth would have retained a different mass and composition. The collision added significant material to our planet, while also blasting away some of Earth's original matter, particularly from its outer layers. A moonless Earth might have been slightly smaller, with a different distribution of elements. Some scientists theorize that the impact contributed substantial iron to Earth's core, potentially strengthening our planet's magnetic field. Without this addition, Earth's magnetosphere might have been weaker, offering less protection from solar radiation. The impact also likely affected Earth's initial rotation. The early Earth is thought to have been spinning much faster before the moon forming collision, possibly completing a rotation in just 5 or 6 hours. The impact altered this spin, and over billions of years, lunar tidal forces have further slowed Earth's rotation to our current 24-hour day. A moonless Earth would likely still be spinning much more rapidly, with days perhaps lasting only about 8 to 10 hours. This faster rotation would create stronger Coriolis effects, dramatically altering global wind patterns and ocean currents compared to our world. Perhaps the most significant difference would involve Earth's axial tilt and its stability. Our moon exerts a gravitational influence that helps stabilize Earth's tilt at about 23.5 degrees relative to its orbital plane. Without the moon, computer models suggest that Earth's axial tilt would vary chaotically over millions of years, potentially ranging from 0 to as much as 85 degrees. This would create wildly unpredictable seasons and climate patterns, unlike anything in our planet's actual history. To understand the implications of this axial instability, consider Mars. With only 2 tiny moons exerting minimal stabilizing influence, Mars has experienced dramatic changes in its axial tilt over time. These variations are believed to have contributed to its extreme climate shifts, including periods when its polar ice migrated toward the equator. On an alternate moonless Earth, similar axial wobbling would create climate fluctuations far more extreme than the ice ages and warm periods of our actual geological record. These basic physical differences would cascade through every aspect of planetary development, creating an alternate Earth that might be recognized as the same planet, but would differ in countless fundamental ways. The most dramatic differences would likely emerge in the development of life. Life on our Earth originated in the oceans somewhere between 3 and 4 billion years ago. While the exact mechanisms remain subjects of ongoing research, Many scientists believe that tidal pools may have played an important role in this process. These shallow basins, regularly filled and emptied by lunar tides, could have concentrated organic compounds and provided cyclical, wet-dry conditions conducive to the chemical reactions needed for life to emerge. On a moonless Earth, tides would still exist due to the sun's gravitational influence, but they would be much weaker, approximately 30 to 40% of their current magnitude. These diminished tides would create smaller, less dynamic tidal zones. Would life still have emerged under these conditions? Possibly, as solar tides alone might still create sufficient conditions, or life might have originated through different mechanisms entirely. However, the specific path and timeline of life's emergence would almost certainly differ. Once established, life's evolution would follow a dramatically different trajectory on a moonless Earth. The chaotic variations in axial tilt would create a planet where climate zones shifted unpredictably over geological time. Regions that were tropical for millions of years might gradually become polar as the planet's tilt shifted, only to return to tropical conditions millions of years later. These massive climate swings would favor organisms with broad environmental tolerances and high adaptability rather than specialized species adapted to stable conditions. The shorter day length would also significantly impact evolution. Plant life would need to adapt to more frequent day-night cycles, potentially developing different photosynthetic mechanisms optimized for shorter light periods. Animal behavior would evolve around these compressed diurnal cycles, perhaps favoring species that could function effectively with different sleep patterns than those that evolved on our longer day Earth. Ocean circulation, crucial for nutrient distribution and climate regulation, would differ substantially due to both the reduced tides and the effects of faster rotation. The specific patterns of upwelling that support highly productive fisheries in our world might not exist or would occur in different regions. Marine ecosystems would develop different structures, potentially with different foundation species forming the basis of food webs. Coastal ecosystems would be particularly transformed. Without strong lunar tides, the extensive intertidal zones that characterize our Earth's shorelines would be greatly reduced. The diverse communities of organisms that have evolved to thrive in these transitional zones, from barnacles and mussels to tide pool fishes and specialized plants, would either never evolve or would exist in more limited forms, adapted to the smaller tidal ranges created by solar tides alone. The evolutionary timeline would likely feature different pulses of diversification and extinction than our actual fossil record shows. The chaotically varying climate might create more frequent extinction events as environments shifted unpredictably, preventing the long periods of relative stability that allowed some lineages to diversify extensively on our Earth. Alternatively, the constant environmental flux might drive faster evolutionary innovation, potentially accelerating the development of novel adaptations. Would complex multicellular life still evolve? Almost certainly, given enough time and the fundamental creativity of evolutionary processes. Would that complex life eventually include intelligent species capable of civilization? This becomes more speculative, but the potential remains, though the path and timing would differ significantly from our own evolutionary history. If intelligent, civilization-building life did emerge on this alternate Earth, its cultures and technologies would develop in response to very different planetary conditions. Consider how human civilizations on our Earth oriented themselves, using the moon as a timekeeper, navigation aid, and cultural touchstone. Societies on a moonless Earth would develop different calendrical systems, perhaps based solely on solar observations or stellar patterns. Agriculture, fundamental to the development of settled human civilizations, would face different challenges and opportunities. The unpredictable long-term climate shifts caused by axial wobble would make intergenerational agricultural knowledge less reliable. Farming practices that worked for centuries might gradually become unsuitable as the planet's tilt changed. This might favor more nomadic societies or necessitate more adaptable agricultural systems with greater crop diversity as insurance against changing conditions. scientific understanding would advance along a different trajectory as well. The Moon has provided humans with a readily observable celestial laboratory, offering clear evidence of impact processes and a preserved record of the early solar system. Without this accessible example of another world, astronomy and planetary science might have developed more slowly or differently. The absence of lunar eclipses would remove an important early tool that helped ancient astronomers understand celestial mechanics and the relative positions of Earth, Moon, and Sun. Even the path to space exploration would differ. In our history, the Moon served as both inspiration and initial destination for human ventures beyond Earth. The Apollo program, which first took humans to another world, provided technological developments, scientific knowledge, and cultural impacts that have shaped our subsequent relationship with space. A civilization on a moonless Earth might focus their early space exploration entirely on the planets, facing the much greater challenges of interplanetary travel without the intermediate step of lunar missions. The physical appearance of this alternate Earth would differ in ways immediately apparent to any observer. The night sky would be darker, but more star-filled without lunar light washing out fainter stars. Coastlines would show less dramatic differences between high and low tide. The day would pass more quickly, with sunrise to sunset occurring in perhaps just 4 or 5 hours instead of the 12+ hours of daylight we experience at middle latitudes during equinoxes. Weather patterns would be substantially different due to the faster rotation and its effects on atmospheric circulation. The Coriolis force, which deflects air masses and ocean currents based on Earth's rotation, would be stronger. This might result in more numerous and possibly more intense storm systems, different prevailing wind patterns, and altered distributions of rainfall. Climate zones might be arranged in bands even more distinct than on our Earth, with sharper boundaries between them. These different physical conditions would eventually shape the distribution of ecosystems across the planet. The placement of deserts, forests, grasslands, and other biomes would follow different patterns than on our Earth. Some familiar ecosystem types might never emerge, while novel ones with no equivalent on our planet might develop in response to the unique conditions of a rapidly rotating world with chaotically varying seasons. The ocean's role in this alternate Earth deserves special consideration. With reduced tidal mixing and different circulation patterns, marine chemistry and biology would develop along different paths. Ocean stratification might be more pronounced, potentially creating more extensive oxygen minimum zones, where certain specialized forms of life might thrive, while others could not survive. The boundaries between major ocean currents might be sharper, creating more distinct marine provinces with less exchange between them. Viewed from space, this moonless Earth would still be recognizable as a blue planet with white cloud patterns, green and brown continents, and polar ice caps, at least during periods of moderate axial tilt. Yet closer observation would reveal a world turning noticeably faster than our Earth, with different cloud patterns and potentially different distributions of ice, vegetation, and deserts, depending on the axial tilt of that particular epoch. Would life on this alternate Earth be more or less diverse than on our actual planet? This question has no simple answer. The more variable climate conditions might reduce diversity by preventing the development of highly specialized species adapted to narrow environmental niches. Conversely, the constant environmental flux might drive faster evolutionary innovation and create more opportunities for adaptive radiation as conditions changed. The total biodiversity might be similar to our Earth, but distributed differently, with fewer specialist species and more generalists with broad environmental tolerances. The absence of strong tides would particularly affect certain evolutionary innovations. The transition of vertebrate life from water to land, for instance, might have followed a different pathway without extensive intertidal zones serving as transitional environments. The specific lineages that made this crucial evolutionary step might have been different, potentially altering the entire subsequent history of terrestrial vertebrate evolution, including the pathway that eventually led to humans on our Earth. Considering intelligent species specifically, if something like humans evolved on this alternate Earth, how might they differ from us? Obviously, they would be adapted to the faster day-night cycle, perhaps requiring less continuous sleep or different sleep patterns. Their psychology might be shaped by different relationships to time, with the rapid passage of days and the absence of the monthly lunar cycle creating a different temporal framework for experiencing the world. Without the moon as a cultural reference point, their mythologies, religions, and cultural expressions would develop around different natural phenomena. Perhaps the visible planets would take on greater significance, or possibly the daily solar cycle would become even more central to cultural organization than it has been in human societies. Different constellations might emerge as important markers due to the absence of lunar light that sometimes obscures fainter stars in our sky. The technologies developed by civilizations on this alternate Earth might emphasize different priorities based on their planetary conditions. The more variable climate might drive earlier development of technologies for environmental prediction, control, or adaptation. The faster rotation might make certain forms of global transportation or communication more challenging, potentially leading to more regionally distinct technological traditions before any global unification of knowledge. Would such civilizations develop space travel? There's no reason to think they wouldn't, given sufficient time and stability. However, their pathway to the stars would differ from ours. Without the moon as an obvious first destination, they might focus longer on Earth orbit, potentially developing more extensive orbital infrastructure before attempting planetary missions. Their first ventures to other worlds would face the much greater challenges of interplanetary distances, without the relatively easier target of a large, close moon for initial exploration. Perhaps the most profound difference would involve the philosophical and spiritual development of intelligent life on a moonless Earth. Human consciousness has been shaped by the experience of the lunar cycle, the moon's changing yet predictable face providing one of our most accessible examples of constancy within change. Cultural concepts of renewal, cyclic time, rebirth, and transformation have often been linked to lunar observations. Without this cosmic timekeeper and its visible transformations, how might consciousness develop differently? What alternative natural cycles might provide metaphorical frameworks for understanding change and continuity? The very concept of Earth as a planet might emerge differently for intelligent species on a moonless world. For humans, observing the moon as another world helped establish the conceptual framework for understanding Earth itself as a celestial body. Without this readily visible example of another world, the planetary nature of Earth might take longer to recognize, potentially delaying the development of accurate cosmological models. All of these differences cascade through time, creating an Earth that follows an entirely different developmental trajectory than our own. Yet despite these profound differences, certain fundamentals would remain. The planet would still orbit the Sun in the habitable zone, still have water, still have geological processes driven by internal heat and plate tectonics. Life would still emerge and evolve, finding endless creative solutions to the challenges presented by planetary conditions. Intelligence might still develop, with beings capable of contemplating their world and eventually reaching beyond it. This thought experiment reinforces how contingent our particular Earth's history has been on the presence of our unusually large moon. The actual path that led to our current world, with its specific balance of conditions favorable for complex life, depended crucially on having the moon as a stabilizing partner. Without it, Earth would still be Earth, still potentially life-bearing and fascinating, but fundamentally different in countless ways that would compound over billions of years of planetary evolution. There are Earths out there without moons, but none of them are ours. The specific world we inhabit, with its particular history, climate patterns, evolutionary pathways, and conditions suitable for human civilization, is inextricably linked to the presence of our lunar companion. In contemplating a moonless alternative, we gain greater appreciation for the cosmic partnership that has shaped our actual planetary home and made it the extraordinarily life-friendly world that we know. The moon is leaving us slowly. we just haven't noticed yet. Throughout our exploration of the moon's influence on Earth and the consequences of its hypothetical disappearance, we have implicitly assumed the moon as a constant presence, a celestial partner that has been and will continue to be part of Earth's cosmic arrangement. Yet the reality is more nuanced and, in the grandest timescales, more melancholy. The moon is already in the process of leaving us, engaged in an imperceptibly slow but inexorable retreat from Earth that began billions of years ago and will continue into the distant future. This departure is not the stuff of science fiction or catastrophe, but a natural consequence of gravitational physics. The mechanism driving the moon's retreat involves the tidal forces between Earth and Moon, the same forces that create our ocean tides. As Earth rotates, it drags its tidal bulges slightly ahead of the Earth-Moon line. These offset bulges exert a gravitational torque on the Moon, transferring some of Earth's rotational energy to the Moon's orbital energy. The result is twofold. Earth's rotation gradually slows, lengthening our days, while the Moon gains energy and spirals outward into a wider orbit. This process is happening right now, at the rate of approximately 3.8 centimeters per year, a distance roughly equal to the growth of a fingernail. This may seem insignificant compared to the Moon's average distance of 384,000 kilometers, but over geological timescales, it adds up to substantial change. Ancient tidal rhythmites, geological formations that preserve tidal patterns from hundreds of millions of years ago, provide evidence that the Moon was indeed closer to Earth in the distant past, creating stronger tides and faster cycles. When the Moon first formed approximately 4.5 billion years ago, it orbited much closer to Earth, perhaps as little as 20,000 kilometers away, looming enormously in the primordial sky. The tides it raised then were hundreds of times stronger than today's tides, sculpting Earth's early coastlines with tremendous energy and potentially playing a role in the environmental conditions that eventually allowed life to emerge. Looking forward rather than backward, what does the Moon's continued retreat mean for Earth's future? How will our planet evolve as its companion gradually moves farther away, its gravitational influence slowly diminishing? This question invites us to extend our time horizon far beyond human civilization, even beyond the typical scales of geological thinking, into the truly deep future of our planet. In the relatively near term, the next few million years, the effects will be subtle and largely imperceptible to anything but the most precise measurements. Day length will continue to increase, adding approximately 1.7 milliseconds per century. Tidal ranges will gradually decrease as the Moon's gravitational pull weakens with distance. These changes will unfold too slowly to disrupt ecosystems or human societies, allowing for gradual adaptation rather than crisis. As we look further ahead, to timescales of hundreds of millions of years, the changes become more significant. The lunar retreat will slow somewhat as the specific resonances between Earth's rotation and the Moon's orbit shift, but the overall trend will continue. Days will lengthen toward 25 hours and beyond. Tidal ranges might decrease by 10 to 20%, gradually altering coastal geomorphology and intertidal ecosystems. Species will adapt or migrate as their habitats evolve, but the changes will likely remain within the range that evolutionary processes can accommodate. The Moon itself will appear slightly smaller in the sky, though this change would only become noticeable to the naked eye over millions of years. Total solar eclipses, where the Moon perfectly covers the solar disk, will gradually become less perfect and eventually impossible as the Moon's apparent size decreases below that of the Sun. This astronomical shift might seem minor, but it would end one of the most spectacular celestial phenomena visible from Earth's surface, a cosmic alignment that has inspired awe and advanced scientific understanding throughout human history. It is when we extend our vision to the truly far future, billions of years ahead, that the full story of the Earth-Moon relationship reveals itself. Calculations suggest that the tidal interaction will eventually drive the Moon to a distance of approximately 550,000 kilometers from Earth, about 1.4 times its current distance. At this point, a new type of equilibrium begins to emerge. As the Moon retreats, Earth's rotation continues to slow. Eventually, Earth will rotate so slowly that its day matches the length of a lunar month, approximately 47 of our current days. At this point, Earth will keep the same face toward the Moon, entering what astronomers call a tidal lock, similar to how the Moon currently keeps the same face toward Earth. Once this occurs, the tidal bulges will align directly with the Earth-Moon line, eliminating the torque that drives the Moon's outward spiral. This configuration, with Earth and Moon mutually tidally locked, represents a minimum energy state for the system, a gravitational equilibrium where the transfer of rotational energy ceases. The Moon's outward journey would effectively end, stabilizing at this greater distance. Earth would experience perpetual daylight on one hemisphere and perpetual night on the other, with a twilight band around the terminator line. The Moon would appear fixed in the sky when viewed from the Earth-facing hemisphere, while it would never be visible from the opposite side. However, this neat conclusion to the Earth-Moon dance is complicated by the presence of the Sun. Solar tides will continue to affect both bodies, potentially preventing the perfect tidal locking described above. Additionally, the Sun itself will undergo dramatic changes during these vast timescales, evolving into a red giant phase that will profoundly alter the entire inner solar system, including the Earth-Moon system. Current stellar evolution models suggest that the Sun will begin its red giant phase in approximately 5 billion years, swelling to hundreds of times its current size. This expansion will engulf Mercury and Venus, and while Earth might narrowly avoid direct consumption, it will be subjected to intense heat that will render it uninhabitable, boiling away the oceans and potentially stripping away portions of the atmosphere. The fate of the Moon during this solar transformation remains somewhat uncertain. The Sun's expanded size will create stronger solar tides on both Earth and Moon, potentially disrupting their gravitational relationship. Some models suggest that the altered gravitational dynamics might actually reverse the Moon's outward migration or destabilize its orbit entirely. Others indicate that the Earth-Moon system might survive as a pair, though transformed by the Sun's evolution, and perhaps ejected into a wider solar orbit by the mass loss of the expanding Sun. Assuming the Earth-Moon system does survive the Sun's red giant phase, their mutual orbital evolution would continue in the transformed environment of the post-red giant solar system. The dynamics would depend on their new orbital position relative to the Sun's remnant, likely a white dwarf after the red giant phase ends. The tidal interactions between Earth and Moon would continue, though potentially altered by the changes to both bodies during the Sun's transformation. In the most extreme far future scenarios, extending tens of billions of years, the ultimate fate of the Earth-Moon system becomes intertwined with the evolution of the galaxy itself. The Moon's current retreat from Earth will have long since stabilized, but new factors come into play. Gravitational interactions with passing stars, which are extremely rare in the current epoch, become statistically significant over these vast timescales. Such encounters could potentially disrupt the Earth-Moon system, separating the pair or altering their orbits unpredictably. The scenario we've explored, following current physical models to their logical conclusions, reveals something profound about the Earth-Moon relationship. What we experience as a permanent celestial arrangement is actually a temporary phase in a much longer cosmic story. The Moon was not always where it is now, and it will not remain there indefinitely. The familiar lunar presence that has shaped Earth's development, influenced countless species, and inspired human culture represents just one chapter in an ongoing narrative of gravitational evolution. This perspective adds a certain poignancy to our consideration of the Moon's disappearance. In a sense, the Moon is already disappearing, not through some catastrophic event, but through the gradual operation of the same forces that have made it such an important influence on Earth's history. The current Earth-Moon relationship, with its particular tidal patterns, its specific lunar appearance in our sky, and its stabilizing influence on our planet's axial tilt, represents a specific moment in a dynamic system rather than a permanent arrangement. For any intelligence arising on Earth, many billions of years in the future, after the Moon has retreated to its maximum distance, many of the lunar influences we've discussed throughout this documentary would be diminished. Tides would be weaker, the Moon would appear smaller in the sky, and its stabilizing effect on Earth's axis would be reduced. That future Earth would naturally experience some of the same changes we've speculated would occur if the Moon disappeared suddenly, but arrived at gradually through natural processes rather than through catastrophic removal. This very gradualness makes all the difference for life and planetary systems. While a sudden disappearance would create shockwaves through Earth's physical and biological systems, the Moon's natural retreat happens slowly enough that adaptation can occur concurrently with the changes. Evolution has sufficient time to adjust to the gradually shifting conditions, and even Earth's physical systems can find new equilibria as the changes unfold. The difference between catastrophic change and gradual transition lies not just in the end state, but in the time available for adaptation. For humans and our descendants, the Moon's retreat will remain imperceptible within individual lifetimes, or even across the entire span of our civilization thus far. Only through scientific measurement can we detect this cosmic drift, this slow farewell between planetary neighbors. Yet knowing about this process changes our relationship with the Moon, adding a dimension of impermanence to what might otherwise seem eternal. The Moon becomes not just a celestial object, but a traveling companion on a very long journey, one whose path is gradually diverging from our own. There's a certain cosmic symmetry to the Moon's story. Born from a catastrophic collision in Earth's early history, it began its life close to our planet, exerting enormous tidal influences that may have helped shape conditions conducive to life's emergence. Over billions of years, it has retreated to its current position, where its gravitational effects provide a moderate stability that has proven advantageous for complex life and eventually civilization. In the far future, it will retreat further, gradually relinquishing some of its influence over Earth's systems. This arc from intense interaction to gradual separation traces a kind of relationship life cycle played out on a planetary scale. From a philosophical perspective, the Moon's gradual departure might serve as a cosmic memento mori, a reminder of impermanence even at the grandest scales. Just as individual lives have beginnings, middles, and ends, so too do the relationships between celestial bodies. What feels permanent to us, due to our limited temporal perspective, is revealed as transitory when viewed through the lens of deep time. The Moon has not always been as it is, nor will it remain so. This recognition of cosmic impermanence can inform our appreciation of the current Earth-Moon relationship, highlighting its specialness precisely because it is a temporary arrangement rather than an eternal one. For those interested in the very long-term future of humanity or its descendants, the Moon's gradual retreat presents both challenges and opportunities. The diminishing of tidal forces and potential increases in axial wobble over billions of years might eventually create less favorable conditions on Earth's surface. However, these changes would unfold so gradually that an advanced civilization would have ample time to develop adaptations, whether technological, biological, or social. Additionally, the retreating Moon would eventually reach a distance that might make certain types of lunar development more challenging. But this too would occur so slowly that navigation and transportation technologies could evolve in tandem with the changing distance. The Moon's retreat also carries implications for our understanding of other planetary systems. Astronomers have discovered thousands of exoplanets orbiting other stars, and many of these worlds likely have moons of their own. The recognition that Moon-planet relationships evolve significantly over time suggests that what we observe in these distant systems represents snapshots of dynamic processes rather than static arrangements. A seemingly moonless exoplanet might have had a significant satellite earlier in its history that influenced its development, while a planet currently orbited by a large moon might experience very different conditions billions of years in its future. As our exploration of the Moon's influence on Earth concludes with this look toward the distant future, we find ourselves completing a journey that has traversed billions of years, from the moon's violent birth to its gradual retreat into the deep future. Throughout this vast time span, the moon has been not merely a passive satellite, but an active participant in Earth's story, influencing everything from our planet's physical characteristics to the evolution of life and the development of human culture. The moon's eventual distancing from Earth reminds us that even the most seemingly permanent cosmic arrangements are actually dynamic, evolving systems. What appears fixed and eternal from our limited human perspective reveals itself, when viewed through the lens of deep time, as a temporary configuration in an ongoing dance of gravitational physics. The Earth-Moon relationship we experience today, which has been so crucial to creating the conditions for complex life and human civilization, represents just one chapter in a much longer cosmic narrative. Perhaps there is wisdom in recognizing both the profound influence the moon has had on Earth's development and the inevitability of its gradual separation. We live in a particular moment in the Earth-Moon story, one that has proven remarkably favorable for the emergence of complex life and consciousness capable of appreciating this relationship. That this arrangement is temporary on the grandest scales does not diminish its significance, but rather highlights how fortunate we are to exist during this particular phase of our planet's relationship with its celestial companion. The moon is leaving us slowly. We just haven't noticed yet. But in understanding this gradual departure, we gain a deeper appreciation for the moon's current presence and its profound role in shaping the world we know. Whether contemplating its sudden disappearance or its gradual retreat, we recognize anew how interwoven our planet's story is with that of its faithful companion, the Silver Wanderer, that has illuminated our nights, inspired our imagination, and helped create the very conditions that allowed us to evolve and thrive on this blue world. If the moon disappeared, the world would not end, but it would feel emptier. Sleep now, under its quiet glow, while it still watches over us. And dream, not of endings, but of light that once was. As our journey through the moonless Earth comes to a close, we return to the present moment, to the world as we know it, with our faithful satellites still gracing our night sky. We've traveled through time and possibility, exploring how profoundly the absence of the moon would transform our planet and our experience of living upon it. Now, as we conclude, let us pause to appreciate the silver light that still shines down upon us, the cosmic companion that has shaped Earth into the world we call home. Look up on a clear night, and there it hangs, a luminous presence that has witnessed the entire human story. The same moon that illuminated the paths of our earliest ancestors now shines down on our cities and technologies. The same gravitational embrace that has gradually slowed Earth's rotation and stabilized its axial tilt continues to orchestrate the tides that rhythm our shores. The same cratered face that inspired ancient myths and religions now inspires scientific exploration and dreams of cosmic habitation. In contemplating the moon's absence, we have gained a deeper appreciation for its presence. Like so many aspects of our world, the moon's value becomes most apparent when we imagine its loss. The subtle yet profound ways it has shaped Earth's development, from the planet's physical characteristics to the evolution of life and the flourishing of human civilization, reveal a cosmic partnership of extraordinary consequence. The moon is not merely a decorative light in our sky, but a fundamental influence on Earth's habitability. The stability it provides to our climate, the tidal rhythms it creates in our oceans, the braking effect it exerts on Earth's rotation, all have contributed to creating conditions favorable for complex life. Without ever intending to, this airless, lifeless world has helped make our planet the living, breathing Earth we know. For human experience specifically, the moon has been a constant yet changing presence, modeling transformation with impermanence through its regular cycle of phases. It has provided illumination in darkness, both literally through its reflected sunlight and metaphorically through its inspiration of art, science, spirituality, and exploration. It has given us our concept of the month, bridging the day and the year in our organization of time. It has been a universal cultural reference point visible to all humans, regardless of geography or historical era. There is something profoundly reassuring about the moon's presence, a cosmic constancy in an otherwise changing world. Yet, as we've discovered, even this relationship is not truly permanent, but represents a particular moment in an ongoing gravitational dance. The moon continues its slow retreat from Earth, a departure imperceptible within a human lifetime, but inevitable across the deep time of planetary evolution. Perhaps this recognition of impermanence makes our current relationship with the moon all the more precious. We exist during a specific chapter of Earth's story, one where the moon's distance, size, and influence happen to create conditions particularly favorable for complex life and human civilization. This cosmic coincidence, this fortunate moment in the planetary narrative, deserves our wonder and appreciation. The moon has been humanity's first step beyond Earth, the initial destination of our species' ventures into the cosmos. The Apollo missions that took humans to the lunar surface represented not just a technological achievement, but a transformation in human perspective. Those expeditions returned not only moon rocks and scientific data, but also photographs of Earth from space, images that revealed our planet's beauty, unity, and isolation against the black void. In reaching for the moon, we discovered Earth anew. As we look to the future, the moon may once again become a stepping stone, this time not just for brief visits, but for more permanent human presence beyond our home planet. Plans for lunar bases, resource utilization, and scientific outposts suggest that the Earth-Moon relationship may be entering a new phase, one where human activity extends this ancient gravitational partnership into conscious cooperation. Yet even as we contemplate this expansion, the moon retains its mystery. Despite being our nearest celestial neighbor, despite being visited by human explorers and numerous robotic missions, the moon still holds secrets about its formation, evolution, and relationship with Earth. It remains a world of discovery, with each new mission revealing unexpected findings about our cosmic companion. If the moon were to disappear, Earth would continue its journey through space. Life would adapt to the altered conditions, finding new evolutionary pathways in response to the changed planetary dynamics. Human civilization would adjust its technologies, cultures, and social systems to the transformed world. But something profound would be lost, a cosmic relationship that has helped make Earth the world we know and love. The emptiness in our night sky would mirror a more subtle absence in our planetary systems, and perhaps in our human experience as well. The moonless nights would be darker, yet filled with more stars. A different kind of beauty, but one missing the gentle silver light that has illuminated countless human generations. The coastlines would still experience the ebb and flow of tides, but with reduced range and altered rhythm, a more muted breathing of the oceans. The seasons would continue their cycle, but might gradually become less predictable as Earth's axial stability diminished over time. These changes would unfold across different timescales, some immediate and dramatic, others so gradual that only future generations would perceive their full manifestation. Yet together, they paint a picture of a transformed Earth, still our planet, but altered in countless ways, both obvious and subtle, by the absence of its cosmic partner. As our exploration concludes, we return to the present reality, to a world still blessed with the moon's presence. Let us carry forward a new appreciation for this celestial companion, a deeper understanding of its profound influence on our planet and our lives. The next time you stand beneath the moonlight, consider the countless ways this silent presence has helped create the world around you and the very conditions that allowed you to exist within it. Look up at the cratered face that has witnessed the entire human story, the cosmic companion that has shaped Earth's development since its violent birth over 4 billion years ago. The moon remains, for now, our faithful celestial friend, illuminating our nights, orchestrating our tides, stabilizing our planet's motion, and inspiring our continuing journey into the cosmos. If the moon disappeared, the world would not end, but it would feel emptier. Sleep now under its quiet glow while it still watches over us, and dream not of endings, but of light that once was.